All right, welcome everyone. Let's get started. My name is Sharon White. I'm the marketing manager for BLT. Welcome to today's workshop, the 3 V's, Vitis Versal and Vivado, sponsored by AMD Xilinx. Before we get started, I just want to take a few minutes to introduce BLT, our team, and to go over some housekeeping. Our class today is from 10 to 3 Eastern Time. We'll have a break around noon or about 2 hours into the workshop. This class will include lectures and demos, and we encourage questions, so if you have them, please put them in the chat panel. There will be no books or PDFs or labs offered with this workshop, but we will send you the recording. The workshop is awareness training. Our regular classes are proficiency training and do include books and hands-on labs. So if that's something you're interested in, please check out our course calendar. Okay, so first let me introduce BLT. We're an AMD Xilinx premier partner and authorized training provider. BLT has been in the engineering design services business for over 30 years, and we were founded by one of the original Xilinx FAEs. Our headquarters is here in Maryland, and we also have an office in Melbourne, Florida. We design chips, boards, software, and complete systems for commercial, military, and intelligence clients. Our designs are in space, undersea, and everywhere in between. And just to highlight some of our more famous projects, we helped design HD TV and satellite radio, and we did one of the first RF SOC designs ever. And we bring that real world experience into our classrooms. Our training is taught by our expert engineers. We've been teaching AMD Xilinx training for over 25 years, and our classes are offered online, in person, and we have private training both at your location or here at our training facility. In fact, we actually have 2 classes running right now in our training center, so it's a very busy day today. That does not include this workshop. We have a lot going on. So if you have any questions about what we do with our engineering design services or training, our contact for that is Lisa Weaver, and I will put her information into the chat panel for you. Monitoring today's chat panel is myself and also Ellie. He is one of our engineering managers, and he'll help answer your questions in chat as well as me. And without further ado, our instructor today is Nathaniel Sokolow. Nathaniel is a project engineer at BLT working on AMD Xilinx UltraScale FPGA and RF SOC applications for defense applications. Before coming to BLT, he worked on radar and electronic warfare applications for several years. He has also worked on and led design projects involving a wide array of FPGA and SoC applications, ranging from PCB design to SoC software, including PCB design and verification using EDA tools, RTL design and verification, SoC boot flow, and embedded software design. So welcome, Nathaniel.
Good morning, everyone. Here at BLT, we work with a lot of people, both our clients and our students. And one common question we've been getting a lot is, what are these Vivado and Vitis tools, and how do they relate to these Versal devices? So the goal of this workshop is to provide some background for the roles that the Vivado and Vitis tools play and the differences between them, and describe the Versal device family. The Vivado portion of this workshop will focus on the design flows, meaning the ways that the user can interact with the Vivado tool for their hardware designs. And the Vitis discussion will describe interacting with the Vitis tool when designing software, as well as the role device drivers play in the interaction between software and hardware. And finally, we'll discuss the Versal device family architecture, as well as the design tool flow used for Versal devices, which is a little bit unique, but we'll talk about that. Once we complete the material, we're going to take a lunch break. Depending on your time zone, this might be breakfast, lunch, or dinner. And after lunch, we'll return and perform some hands-on demos with the Vivado and Vitis tools, as well as a basic demo of what designing for Versal devices looks like. So without further ado, let's begin the workshop. The first thing we're going to talk about is an overview of embedded hardware development. The Vivado and Vitis tools are the tools used for embedded hardware development, which is an integrated system involving both hardware and software. Versal devices are embedded systems as well. So we will discuss the basic concepts of an embedded design. So what makes an embedded design special? Embedded design consists of many different parts that have to come together and work as a single integrated unit. The two main elements of this are the hardware design and the software design. Hardware design focuses on the processing system, as well as other physical hardware, such as peripherals, memory subsystems, and coprocessors that exist in the system. And software design deals with different levels of software, starting from bootloaders and operating systems, as well as hypervisors, as well as the software applications the user will design for the processor to run. The hardware development environment is the Vivado design suite, which supports both graphical design as well as HDL design. And these two approaches can be integrated together into a single design and often are. The IP integrator suite is the tool that enables users to graphically assemble the embedded, as well as traditional hardware systems that don't involve a processor, based on Xilinx provided IP, and as well as custom user IP. Another tool that can be used for hardware development, and we'll discuss how these tools interact, is System Generator, which allows MATLAB-driven generation of code and binaries to be implemented in programmable logic. And these can be built into IP to be integrated into a traditional hardware system. There is also high-level synthesis, or HLS. High-level synthesis supports converting software code, C or C++ code, into logic. This allows the user to build designs driven by software and is great when the designs are based on algorithms or numerically intensive, which aren't necessarily things that are always simple to do in hardware description languages. The most common case of HLS is for accelerators, which are a topic, hardware acceleration is a topic we'll be covering. And coprocessor in this context is an alternative term for accelerator. These HLS outputs are then imported into Vivado and integrated together with your hardware designs. Once the hardware is done, the Vitis IDE is used. Vitis is a software development environment which integrates with the other Xilinx tools. There are a lot of configuration options for an embedded system. These configuration options can include different peripherals, such as communication interfaces or other peripherals, memory configurations, programmable logic that the user will write or IP, and different processor accelerators for all sorts of applications. These designs may involve both the programmable logic and the processor, or an embedded design may only use the programmable logic. Programmable logic can also contain soft processors, such as the microblaze, which can perform some of the functions that a traditional processor would. Let's review the traditional embedded development flow. Typically, there are different engineers who would be involved in embedded development. You can have someone working on the software development, someone working on the hardware side, and a system architect who will design the interfaces for the hardware and software to interact with each other, as well as external interfaces. An additional element that can become part of the traditional development flow is HLS. High-level synthesis allows using C or C++ to perform certain elements of the hardware creation. as well as provide accelerators, which the software can leverage for higher performance software applications. The first question whenever designing software for an embedded system is, does this system need to be real-time or have a real-time component? Real-time systems have different requirements than systems that do not necessarily need to operate in real time, as different processors or hardware might be used. Is an operating system necessary? There are trade-offs. A bare metal system may be simpler and easier to use, but it might be less capable. Are multiple processors required to meet the performance requirement? This can sometimes provide higher performance, but add complexity, and perhaps a hypervisor should be used. The system architect is the person responsible for partitioning the hardware and software components of the system. Many tasks can be done in both hardware and software, and there are trade-offs when doing this. Software is more capable in certain ways and hardware is more capable sometimes, and the system architect needs to balance the lower performance but ease of development for a software implementation, along with the typically more challenging but higher performing hardware implementation. Sometimes a higher performance is worth the additional design complexity and potential overhead time, and sometimes it isn't. And the system architect should be the person deciding whether it is worth trying to do it in hardware or not. It's easier to do everything in software than to build hardware, but processors do not offer the same processing capability as dedicated hardware, so a balance needs to be struck. Additionally, the system architect should identify what the system needs to do and how well it must do it, which are the behavioral and performance specifications, along with other limitations of the system, such as, does the system need to run on battery? Is power consumption a high priority? And other key elements of the system, as well as, well, what does this design need to connect to, and how do I need to structure these interfaces? With all that, the system architect, with the input of the hardware and software engineers, can pick the family of devices best suited for any particular design. The part of the embedded design process involves choosing peripherals and memory subsystems, which are key elements of any design, as well as major contributors to the performance and capability of these designs. These major blocks are connected to the processor via the AXI interconnect. Typically, the user will configure these peripherals and subsystems for whatever exactly they need it for. Once everything is connected, the user can validate the design and start testing it. Here's an overview of the hardware development process. The Vivado design suite is specifically designed to facilitate hardware design. Vivado will be used for both embedded and non-embedded designs, which can be a pure logic or software and hardware integrated design. Some of the key parts of the hardware development process in Vivado are simulation, which will run software model behavior as shown in the waveform and can be run at different points in the development cycle. Simulation is important because often there is far less overhead on testing your design and simulation, both in terms of access to hardware, as well as in terms of the time it takes to build. Simulation is typically a lot faster. Once a design is simulated and complete, and then the user can begin to build the design and hardware. The key elements of this are synthesis and implementation. The first part of this is synthesis, which will transform the HDL into a low-level netlist. These netlists are then mapped to implementable resources in the design, and then implementation is run in order to map the resources that have been synthesized to the parts of your FPGA. The tools can synthesize both VHDL and Verilog. Finally, after the design has been converted to the hardware, the bitstream is generated. This bitstream is the programming or configuration file that can be used to configure the target device. During development and debugging, this will often be loaded directly via JTAG or a similar method. And eventually, typically in a design in the field, the bitstream will be loaded from some sort of flash memory or potentially over a network. So there are multiple tools and flows to develop hardware, which includes both traditional Vivado, where the user will design in HDLs and IP integrator, as well as high-level synthesis and model composer. And simulation and debug cores can be used to debug the design once the design is in hardware. So next we'll talk about design flows. Design flows are the way the user interacts with the Vivado design suite to create their design. We'll describe how the register transfer logic, often implemented as hardware description language, is converted into the programming file using the design flow, and talk about some of the system level integration flows. There are two primary high-level approaches to using Vivado. One is based on RTL to bitstream, where the user will design an RTL file using a hardware description language like Verilog or VHDL, and the tool will then turn this into the bitstream to configure the device. And the other design flow is the system level integration flow, where the user is going to focus on designing their overall system and how the elements of the system interact with each other. The tool will eventually turn both of these into an RTL to bitstream flow. The key difference is the approach the user uses in their design process. In a system level integration flow, typically the RTL is generated based on a more automatic process instead of the user writing that code themselves. Here's the high-level design suite flow. There are a number of different inputs that can be provided to the design suite in order to provide the basic sources used in synthesis and implementation. High-level synthesis inputs can be provided, as well as model composer. Alternatively, the user can write their own RTL code, which they'll often do as part of a project, and include different Xilinx IP from the IP catalog or other sources. All of these inputs, with the exception of RTL development, where this is optional, will be put into the IP integrator block design, which will then configure a system level design. Alternatively, IP integrator can be not used, and an RTL based hierarchical design can just be created and synthesized directly. The system design entry step talks about how you would input, what the options are for inputting these different sources. And then once this is in, the logic is then simulated. Again, this can be both an IP integrator block design and HDL logic, and the functionality is checked. After which, physical and timing constraints are applied in order to enable the tool to translate these designs to hardware. And then synthesis and implementation are run to actually build the design. Once that's finished, time enclosure and other design analysis is performed to make sure that the solution the tool built will meet all of the timing requirements specified in the constraints. And once everything succeeds, a bitstream is generated in order to configure the FPGA with. Independently to this, software is developed in Vitis, as well as an operating system may potentially be built. These things are an independent flow, which will be part of the final embedded platform solution that we'll discuss more in the Vitis section. Here are the primary components of the RTL to bitstream flow. There is a major difference between Vivado and the older tool ISE, that Vivado uses a common data model. which means that there is a database object representing your design, and all of these different processes are run on that object. So what happens is, for example, since design is run on a database object, after which link design and op design will be run on that object to further the process of converting it to hardware, and so on. Another key element here is the XDC constraints, which stands for Xilinx Design Constraint. It makes it easy to apply constraints at any stage in the design flow and conduct real-time debugging and see how the constraints affect different stages of the design. All information is saved in the form of a design checkpoint. So when a step of this process is run on this database object, a design checkpoint can be created. It will save the current state and allow the user to use the previous results to continue the process. This can be very helpful because it can save a lot of time and help allow consistency if you keep using the same design checkpoint. Vivado supports a number of industry design standards, which allow being compatible with different tools or simulators you might use. These standards include TICL, as well as System C, Synopsys Design Constraints, Verilog and VHDL, and including the new VHDL 2008 and System Verilog, and AXI 4 and IP Exact, which are universal industry standards that make it easier to integrate these embedded platforms into a system. The two main flows used in Vivado are project and non-project mode. Project mode is typically a GUI-based approach, although it does support TICL as well. And non-project mode only supports TICL. While TICL does exist in both project and non-project mode, there are many commands that are specific to either project or non-project mode and can't be mixed. So some of these project mode commands can't be used in non-project mode. Project mode will create a project structure on disk, which will create a number of files. The tool will manage the design run status and data. So the tool will automate a lot of the flow. Reports are generated automatically and will always be available even without the user specifically requesting them. And in general, the design environment is very interactive. By comparison, in non-project mode, the project is compiled in memory, TICL-based batch processing, and doesn't save files on your system. Only the files that the user creates that intentionally will be on the system. The design source files must be intentionally managed. And while the GUI does exist in non-project mode to examine different things, it doesn't have all the functionality that project mode has. Here are some of the advantages or disadvantages of project mode versus non-project mode. Project mode is often easier to use due to the high degree of automation. There are flows that are part of project mode that include a number of different steps at once, so the user doesn't need to consider all of the different steps that need to be performed and can just use a higher level synthesis or implementation run to manage that. And the GUI will handle a lot of the source files and results that are created as part of a project. There are advantages and disadvantages to this. The automation can make it a lot easier. On the other hand, a lot of the time the automation can make certain things more difficult, and if the user wants something different, they may not be able to always do that in project mode. Additionally, project mode provides less flexibility of some of the intermediate process results because, for example, it groups implementation as one large implementation process instead of all the different stages to implementation. And there are certain elements that are hard to access. It also makes revision control tricky at times. I'm sure many people here have experienced the process of deciding which files in the Vivado project should be revision controlled and which should not. Non-project mode, on the other hand, can be a little more difficult to use because the user needs to control almost everything and run all the different processes that need to be run, and does require more in-depth knowledge. However, it can be very useful because it provides a lot more control with fine granularity commands, runs quicker, and allows the user full customization. It also, because it doesn't create a bunch of extra files, makes it easier to manage revision control. Here's a summary of project mode advantages. Automatically manages everything. Will store all results, including reports. Project mode also includes some more advanced design analysis capabilities like cross-probing, and supports the creation of multiple runs where the user can have different run configurations in a project to test different options they have. Non-project mode, the user will manage their design manually, which includes source files and dependencies. This provides the user a lot of control and ability to make sure everything is exactly the way they want it to be. And there's an entire suite of tickle commands which allow the user to create and analyze these designs in non-project mode. There is another integration flow, which is the system level integration flow. These include three main different points. There is the embedded processor design flow, where there is hardware designed and there is software designed. And the hardware and software work together towards the embedded design. This is typically considered the traditional embedded design flow. You design your hardware in Vivado, you design your software in Vitis, and you set things up so the software and hardware can leverage each other's capabilities. One tweak to Vivado hardware designs is the dynamic function exchange, or DFX design flow. Sometimes you can have a design where part of it can be reconfigured in real time, which allows your primary design to keep on running while you change certain elements of it in real time without interfering with the base operation of the device. One element that has been being used a lot is the accelerated kernel flow. And the accelerated kernel flow, a Vivado hardware-based platform is created, and then the Vitis software platform can add accelerated hardware kernels to this platform and modify the design, and then allow those accelerated kernels to be accessed by the software. These often can be changed in real time. You can load or unload different kernels. We'll talk about the accelerated kernel flow more when we discuss Versal devices. There are two ways to launch a Vivado IDE. The first one's from the desktop and the other one is from the command line. The command line allows different options. Tickle or batch are command line based options. The difference between tickle and batch mainly is whether batch will shut Vivado down once your script has been run, whereas tickle will keep the Vivado tickle command line open. The Vivado tickle console can also be started using a separate tool in Windows or Linux as well. The other mode is the GUI, the traditional Vivado IDE with the whole user interface. In GUI mode, Vivado will store a log and journal file, which will store the instructions used in the command. In tickle mode, the interactive tickle console will be launched, and in batch mode, a script is run. Here is an image of the design environment with highlighting some of the important windows that might be used. The largest window on the right side is the workspace window, which in this image is showing IP Integrator, the block design tool. You can see on the left windows to show the sources and attributes, as well as the console, which shows different views to see what's going on. All these windows allow the user to get a good picture of different aspects of the design. In summary, the Vivado tool uses a common data model. In order to improve runtime and memory resources, synthesis and implementation are run on a single database object. There are two main use models in project mode and non-project mode. And IP integrator allows for the user to do system level design with block designs. Next, we're going to look more into the project and non-project based flows. We'll focus on project mode and how project mode works, describe the structure of a project and how files are integrated as a part of the project, and talk about how one creates a simple Vivado project in project mode. In project mode, there is a graphical user interface where the flow navigator on the left side can allow the user to configure and run different major design flow steps, such as synthesis, implementation, or bitstream generation, as well as design analysis and reports. When a Vivado project is created, a directory structure is created on the disk, which stores all the files. Typically, if the user doesn't modify this, there will be a project name.sources folder that contains all of the different types of sources. In general, the source files, run results, reports, and general status are all managed automatically. Project mode can be run in either the GUI or Tickle. The user can script everything or can do it in the graphical user interface. These methods can work together as well. What is a project? A project is best viewed as a big picture of the design process. It's a snapshot of everything. It includes your files as well as your generated projects and other project data that tell you more about the status of the project. The project holds all the files as part of the design process, both user-generated and automatically generated. It contains the netlists that are used for synthesis and implementation, and manages all of the project data and processes that are run on the database object for synthesis and implementation. Project mode will save the design state at every step in order to give the user an accurate picture of what's going on in the project right now. So a lot of this is automatic, but the tool provides a lot of information to the user and some degree of control for how the project is going to do different things. The project itself is stored as an XPR file stored in a project directory, which is a project file that when opened in Vivado will open the entire project. There are other subdirectories, including the source directory, as well as generated IP and other output products and simulation files. These subdirectories are, as shown, are created by the tool automatically. The user does have some degree of control over where the source files are being stored, but by default, they'll be created in the sources folder. The project flow provides a much more interactive design environment with a consistent interface, which makes it somewhat simpler to use than scripting often. It allows the user to provide source and run management, IP configuration, as well implementation, as well as analysis and floor planning, and generating bit streams and more. Vivado allows the user when creating a project to choose the specifications of the project. There are different types of projects, what source files the user wants to include, although these can always be added later as well, and what constraints should be applied to the design, although again, these can be modified after the project is created as well. One key element of the project-based flow is the runs manager, which groups a number of different steps into synthesis runs and implementation runs, which means the user has to keep track of much fewer things. These synthesis implementation runs can then be configured as the user prefers. When the user creates a new project in the GUI, there is a new project creation wizard that provides different types of projects. Most of the time, RTL project will be the project the user will design. These are traditional projects where the user will be adding RTL sources or designing an IP integrator flow in order to generate a bit stream. But other notable options are the IO planning project, which allows the user to plan the IO for the pins on their device. This can be very useful when working on a custom PCB and putting an FPGA on where the hardware design is not finished yet, as well as imported projects where old ISE projects can be imported and converted to Vivado. One of the key elements of a project are the file sets. Projects keep a variety of different types of files, which are separated into different file sets. The major file set types are the sources file set, the constraints file set, and the simulation file set. Sources will store the source files, constraints will store the constraints files, and simulation stores simulation files. One example of a case where this might be important is test benches are generally not meant for synthesis, which means that if the tool tries to synthesize a test bench, often there will be a lot of problems with that. So in order to prevent that being an issue, test benches are kept under simulation file sets, which are exclusively used when simulating and not when building the hardware design. Both file sets as well as the files in them are objects. In general, Vivado is a very object-driven structure. Many of the elements of a project in particular are objects. Each of these objects has different properties that can be set or reported depending on the property. And the GUI, most of these can be done through the GUI, but they can also be done through Tcl as well if the user chooses to. The get files command is a good way of listing all the files associated with an object when scripting. Here's an example of how the GUI and Tcl are equivalent. The run synthesis button, which launches a synthesis run, for example, directly correlates to the Tcl command of launch runs synth1, because synth1 is a default synthesis in this case. Same for run implementation and launch runs implementation run. And generate bitstream relates to a flag in implementation. The bitstream is generated as an optional last step to the implementation process. Each of these runs also creates various checkpoints while running and different reports. If runs were not being used, then a lot of these would need to be generated manually. When a project is open in Vivado, there are a number of different windows that can provide information about the project. The project summary can provide a number of key elements of the project that are important when designing, such as the target language, which is what the primary project language is supposed to be, as well as what hardware part the project is meant to be targeted for. These can be changed from this window. If you click on the blue links, it'll open the appropriate settings tab, as well as in the settings menu. On the left, we see the sources window, which besides listing the sources, also provides a hierarchical view as shown. And will show which modules are in the top level, as well as which ones are lower down. And the console will provide the user information about different elements of the project, including design runs, as well as different messages while running some of the design steps. Here's the project settings menu, where all of these parts in the dashboard can be changed if the user would like. There are a number of different settings, which are very extensive and we're not going to go too far into, but to summarize, general includes the general project settings as a whole. The simulation, elaboration, and synthesis and implementation steps include different settings that are specifically applicable to those steps of a run. Same for generating the bitstream, and IP contains IP-related settings. The dashboard is a convenient way to see all of the project settings in one place, as well as many of the other settings. The dashboard is configurable using Tcl if the user wants, and the user can choose which reports should be run. Many reports are optional and only useful under certain situations, while other reports like timing should be run at all times. So the Vivado design suite in project mode manages the whole project and automatically sets a lot of the elements of the project. There are advantages and disadvantages to this. This automation provides less flexibility, but provides often more consistency and automatically manages a lot of the commands. Vivado also supports multiple runs in order to allow easy switching between different build configurations in project mode. The flip side of project mode is non-project mode. We'll discuss using non-project batch mode, identifying the netlist currently in memory and what in memory means, describe how constraints are managed in non-project mode as opposed to project mode where they were simply targeted XDC files, and describe different design analysis commands that can be used in the design in memory. As we mentioned earlier, every build in Vivado consists of a design database, which is the underlying design stored as an object. The different elements of the design operate on netlists. So first an elaborated netlist is created, then the synthesized netlist is created, and finally implementation is created. This allows the user easy ways to get information or alter the database using Tickle in non-project mode. Project mode, these are typically done via the GUI. The system level design flow provides both project and non-project mode. As we discussed project mode previously. In non-project mode, the user controls the fully customizable flow to control every aspect of the backend tools. These include synthesis, netlist optimization, which is logic optimization, power optimization, placement, physical optimization, routing, and bitstream generation. Some of these steps are optional, whereas most of them are required. Once the bitstream is generated, it can then be placed on the silicon. Reports can be optionally generated during this process. In the batch flow, the user has full control. The process runs entirely in memory and doesn't create any additional files. Only the files that the user creates will be there. As a result, there is no disk footprint. This can be very useful on a system where the user is not supposed to be leaving untracked files around. And the user performs all input and output manually. The user supplies the files, the user supplies the instructions for the tool to build, and then the user defines what the outputs of the build are and where to put them. The user also is in full control of which reports and other output elements are generated during this process. This is not exclusive to block designs or anything. The sources the user provides can be traditional HDL files or IP integrator block designs. But the user does need to provide all of that. The flow works as follows. First, the design is read in using read wildcard commands, which are either read Verilog or read VHDL. The synthesized netlist is generated using synth design. All the later processes use the netlist, which was generated during the synthesis process. The design constraints are left open in memory, but they are not stored on the file system. Every process the user wants to run, both in terms of building and in terms of reports, is chosen by the user as a part of options to the Tickle command. And report and visualization commands can be run in memory. The user can look at these outputs in the Vivado GUI, even in non-project batch mode, if the user chooses to. A key element of the build process is the netlist. There are several different netlists that are used, primarily the elaborated, synthesized, and implemented netlist that represent the design at different stages of the build process. At different stages of the build, one of these netlists is selected as the current netlist, which is the netlist as loaded into memory. And this netlist changes its format and contents as the design flow progresses. The elaborated netlist is a generic technology representation of your design, which uses generic logic to create a netlist. The targeted FPGA in the top level are specified as part of the design. And the tickle command for an elaborated design is shown. The synthesized netlist uses FPGA basic elements such as flip-flops or LUTs to represent your design as a part of translating your RTL logic into hardware. And will create the synthesized netlist that the implementation flow will use. Finally, the implemented netlist represents translating basic logic elements into your specific hardware resources. So it maps the generic representation from synthesis onto your specific device. Most operations that can be performed on the synthesized netlist can be performed on the implemented netlist, although often they'll have a greater degree of accuracy because much more information about the final design is available now. And the bit stream is written out based on the implemented netlist. Constraints tell the tool how it should construct the circuit. These constraints can come in both timing constraints as well as other kinds of constraints that can be applied. These constraints must be applied to a netlist. These can be an elaborated netlist as a part of the synthesis, and then read in and used when the tool performs synthesis, as well as constraints that can be read in after synthesis, which can be used to adjust the implementation in later processes. Once synthesis is complete, these post-synthesis constraints are applied to the in-memory design in non-project mode, and reset timing can remove all constraints. And then new ones can be reread in via read XDC. Read XDC allows the user to read an XDC file instead of providing each constraint individually. Constraints should be available for all the different processes involved, which include synthesis, place, physical optimization, and routing, and can adjust how the tool approaches different parts of the build process. These constraints can be the make or break whether the design meets timing, which can heavily affect the reliability of the design. Here are some common non-project mode tickle commands that will more or less always be used in a true non-project mode project. Read Verilog, or the equivalent read VHDL, will read in the HDL files. Synth design will launch the synthesis process. Don't confuse that with the synthesis run. In project mode, the synthesis run includes a number of other things that aren't part of the synth design command. Set param and set property can be used to configure different elements of the project or netlist. And report properties can be run to create a variety of standard reports, the most necessary being the timing report. For later parts of the process, link design will load a design into memory if it's not in memory at the moment. Op design will perform high-level design optimization on the logic. Route design will route the design onto the FPGA. If the write bitstream will write the bitstream. And one key point, you can launch the GUI in a non-project mode script using the start GUI command. This will open the GUI design in memory and allow you to examine things like the netlist in the middle of your script. Summarize, non-project batch mode runs in memory as opposed to on your file system, so it does not create extraneous files as a part of running these processes. In batch mode, constraints are first read in during the synth design process and can be read in during later parts, such as the implementation using the read XDC commands. And non-project mode does provide a lot of advantages with the user being able to choose exactly how they want parts of the designs to run. So I see a question in the chat about constraints. Many times constraints have to be run at specific points during the overall build process. What ensures they are processed in the correct order? Is there guidance which suggests how to segment out constraints into separate files? So as far as separate files go, typically what you would often do is separate different types of constraints. So you would have a file for your IO constraints and a separate file for your timing constraints. This allows you to take a look. It's pretty rare that you would want to have conflicting constraints in different files. You can't, in non-project mode, you can control the order XDCs are, but typically you can set these constraints as part of your synthesis process. So you can run a read XDC command before you run synth design, and then you can run a different read XDC command before you run implement design. And these commands, you can specify the XDC file in Tickle to specify at what point in the non-project mode they're read in. In project mode, you don't always have this much control. So if there really is a specific point, then this is a good example of where the advantages of non-project mode come in. So that is the Vivado portion of this presentation. To go over, we discussed what Vivado is, how the different sources for Vivado can be presented in terms of RTL files, IP integrator block designs, high-level synthesis designs, and model composer. And we talked a little bit about project and non-project mode and the advantages of both, and as well as the limitations. So now that we've talked about the hardware side, the next thing we're going to discuss is the Vitis software development tool. And we'll begin with how the user can drive the Vitis development tool. We'll talk about what the purpose of the IDE is, talk about what makes Vitis special, and the primary capabilities Vitis has to support embedded designs. Xilinx provides the Vitis IDE as a part of the Vitis unified software platform. This IDE is designed to be used for the development of embedded software applications targeted towards Xilinx embedded processors. This IDE is designed to work together with hardware designs that have been created in Vivado. The Vitis IDE is based on the Eclipse IDE, which many people may be familiar with. This IDE is Java-based. Because it's Java-based, Vitis works on both Windows and Linux. The Eclipse platform allows a lot of user customization and supports user add-ins. As a result, Eclipse is an ideal platform to enable Xilinx to add new capabilities, special to FPGA and SoC design. These make code development for these SoC families much easier and include a collection of common templates for things like bootloaders, as well as C and C++ applications. Many of these are automatically added, other ones the user can add themselves. Some of the extensions to Eclipse that have been added in Vitis include bootloader generation. AMD's Xilinx SoC devices need specific bootloaders customized to these devices, and Vitis will generate them for you. Platform management software customized for each SoC platform, as well as more traditional applications like user applications and make files. These tools interface seamlessly with the hardware and support both PS processing system hard processors and soft-core processors implemented in the logic. Here are some other key extensions. Their Vitis, unlike vanilla Eclipse, has some profiling and visualization tools that allow the user to see how their code is performing on the hardware, a system debugger for debugging code running on the FPGAs, and productization, which results in a more polished and well-documented product. Vitis focuses on full platform support rather than collections of applications. Vitis's goal is to be one application that the user is going to use for their software development instead of having 5 different applications that the user needs to do every individual thing on. The user does need to be aware of the full range of applications required to drive the hardware. Vitis organizes information into projects. These projects can be either exclusively software application projects or integrated embedded projects that include both hardware and software elements. One of the goals of the Vitis IDE is to make sure that the amount of information the user is presented with at any time is manageable. Eclipse doesn't have a built-in toolchain, but Vitis includes the GNU toolchain. The user can change this to different toolchains, such as an ARM toolchain or others. All these toolchains have a well-defined path through the tools and require specific files. The compiler will require C or C++ software sources, and will convert them into assembly code, then link them as object code, and eventually create an executable ELF file at the end of the process. The end result of this process is the ELF, which is the executable file. This can be examined using the object dump utility if the user needs to look at the executable. Sometimes there'll be multiple ELF files, one for each processor if it's a multiprocessor system, in which case one of the things the bootloader does is to send the right ELF to the right processor. Let's look over the application development flow. The first thing to develop an application is developing the hardware specification file in Vivado. For an embedded system, the user will usually create custom hardware or can use predefined hardware provided in the Vitis IDE. These can be downloaded and many of them are built in. The details of the hardware construction are covered elsewhere. The important point is that the hardware design is made available to Vitis, either by exporting from the Vivado design suite or by importing from the Vitis IDE. For custom hardware, the user will export a Vivado hardware description. And for pre-generated, they will often be installed as part of Vitis. The Vitis IDE then uses this hardware information as a key component in a platform project. The hardware description specifies things like the number and types of processors, memory capabilities, as well as other resources, and the address ranges for the processor to access different elements of the hardware. Sometimes software will need to begin being developed before the hardware definition. Occasionally, the hardware design may need to be modified based on things the software needs. Some of the higher end devices, such as MP-SOCs, RF-SOCs, and Versal devices, contain sophisticated processing systems, including multiple processors, different built-in peripherals to the processor side, and memory. These platforms have predefined configurations that will allow the coders to begin targeting a processing system, even though their hardware design is not complete yet. A platform project includes both hardware and software. The hardware description is imported from Vivado, or a predefined hardware description is used, but the software is partially described by a domain. The domain describes which processor is running the software. So for example, an MP-SOC has both an A53 and an R5 processor. And the user needs to specify whether they want their software to be targeted to run on the A53 or the R5. Vitis controls this via the domain property. In a platform project, the platform components like boot and platform management firmware are generated automatically based on the hardware specification. Once a platform is defined, then the user can start working on their application for this platform. This is the process of writing the user code. This can be done from a template or from scratch. And there's a system project that contains all applications. There can be multiple application projects in one Vitis project managed via a system project. Once the development is finished for this hardware and software, this code can be downloaded to the physical board, which includes both the programmable logic elements, the bit stream, as well as the processor elements, including the operating system and applications. These typically would be loaded while testing over a JTAG, but in the real application, they would normally be loaded from flash or a similar location. The standard configuration is to build all of the elements of this Vitis project, both the hardware and software, into a single bootable flash image, where the user will just flash a single image onto the memory and use that. Platforms are a description of the hardware element combined with the software and are used to boot and maintain the platform. These include processor cores, memory controllers, and peripherals, both in the processing system and elsewhere. The platform is imported as an XSA Xilinx support archive file that contains a description of the hardware and is typically built using Vivado. There are other ways to do it, but normally Vivado will be used to export a Xilinx support archive for a hardware design. If a modification is made to the hardware, the XSA can be re-imported into the existing project. You don't need to make a whole new project because the hardware changed. You just update the existing software project with the new hardware design. The domain is what specifies which processor or which processors, in cases of an operating system or other isomorphic design, are used to run the application. A domain can include either a board support package or an operating system with a collection of drivers. The board support package is a collection of libraries and drivers that support the processor. BSPs are usually used in standalone applications rather than operating systems and contain different libraries and settings to allow the software to control the hardware. These standalone BSPs are typically single-thread operating systems where there is one processor that is able to do one thing at a time. You do have the ability in Vitis to cluster multiple processors and control them via an operating system if necessary. Every application must have a specified domain, though. The application must be told which processor it's supposed to run on. The system project represent containers for all the applications executing at once. The Vitis project and the processor can have multiple different applications executing as a part of a bigger picture. The system project manages all of these separate applications. In an operating system, the scheduler will context swap the different applications to change which one the processor is executing on at any given time. One other thing are the views. Views allow, as we mentioned, one of the priorities with Vitis is to make the amount of information that the user has access to at any one time more manageable. Views are a good way to control which information the user is looking at. There is a very extensive list of views that can be used from the View tab in Vitis. Configurations can be used to make Vitis more flexible. There are both pre-built default configurations as well as customizable user configurations. A configuration allows a user to specify different settings. So debug can have one set of settings for a build in order to build debug utilities, and run may have a much more trimmed down set of utilities included. The user can also make custom ones unique for specific situations or different applications of the Vitis project or similar. Each configuration is stored in a unique directory. And once a configuration won't be used again, it can be deleted. The three primary configurations are debug, release, and profiling. The debug configuration is used to debug targets. It produces an executable file, but allows code stepping through the code and uses different compiler settings and a run configuration in order to make debug easier. The release configuration, on the other hand, is used for the final release of the software, which contains specific settings for each tool in the toolchain, as well as a set of configurations that are usually used to generate production code. Production code is the application with just the appropriate optimizations and all unnecessary objects removed to lower the footprint. On a real system, things like memory or bandwidth even sometimes may be a concern with including a lot of unnecessary applications. So release trims out all of the debug elements. The profiling configuration is used for performance measurement. Profiling measures the software execution time of each routine or function, and is very good to get a picture of how efficient is the software and do changes need to be made in order to perform the application's purpose. The linker script is an input file to the backend tools. It describes how the different regions of code are supposed to be placed in memory by the linker tool. The linker tool script describes where the entry point into the executable code is located and partitions specific regions of memory for the heap and stack. While it's not required for small contiguous memory designs, sometimes the linker script is important if the memory map is discontinuous at any point. The tool will typically automatically handle the linker script. So generally speaking, the most important thing here is to be aware that the linker script exists. But you typically won't be writing a linker script yourself. One other key element of the Vitis IDE is the ability of the Vitis IDE to assist in software debugging. Debugging is critical because most designs don't work perfectly the first time. These include both the traditional GDB as well as a system debugger that allows the processor to be controlled over JTAG. TCF can be used to debug standalone bare metal applications on the processor, as well as Linux applications or even the Linux kernel itself. These debuggers support all of the standard debugger actions, such as single stepping through each line of code, step over and step out to debug different blocks of code at a time, or continue after breakpoints. Summarize, Vitis is based on the Java-based Eclipse platform. It runs under both Windows and Linux. It's platform independent. There are many add-ons special to Vitis over the normal Eclipse IDE in order to ease software development for the Xilinx platforms. Different types of information are stored as projects. Projects include platform projects, which represent a description of the hardware elements of the design. Application projects, which are single software applications meant to run on the design, and system projects, which are groupings of all the different application projects together and allow a project to manage all of the individual applications. And there are several default configurations that can be used in order to streamline the development process for different purposes. Now that we've gone over software development on Vitis, the logical follow-up question is, how does the software interact with the hardware design? The answer to that question is through device drivers. We'll explain the purpose of a device driver and how the device driver allows the software and the hardware to interact, and describe how these device drivers fit into the general software development scheme. The premise of a device driver is that the device driver is a piece of software that sits at a higher level above the hardware. So there'll be the hardware element, there'll be the user software application, and the device driver is the layer in the middle. The user application will use the device driver to access the hardware. The device driver is aware, as part of the design the device driver, of the peripheral's register set and sequences and timings that commands need to be sent for the device. The driver will make sure that the user application can access the hardware the way it wants to. This is much more elegant than trying to access hardware directly from a user application, which can be problematic for a number of reasons. Often things a device driver will do are, for example, set different parameters that for the addresses of registers in the hardware, as well as the values that can be set to those registers. So a typical example of this would be the driver would specify the reset value and location, and the user application would just send a general reset function, which the driver would translate into the hardware, as opposed to having to write a bit to a specific address. Device drivers come in several flavors. The primary ones are block devices, which represent blocks of data, like a hard drive that is organized as a single large block of data with different addresses in it. Character devices, which handle streams of characters as opposed to address. So a UART is a good example where individual characters are just streamed into the UART. Network devices, where the driver controls packets that can be sent over Ethernet and allow controlling or being controlled by different elements that connect through a network, or pseudo devices, which drive simulated devices that don't exist in the real hardware. There are 3 layers of drivers that are specified for different functions. There are different levels of abstraction that a driver can use to access the hardware. The layer 0 is the layer that is closest to the hardware. This talks directly to the hardware and represents the lowest level drivers. They are usually the simplest, but also the least elaborate drivers. Level 1 drivers are higher level drivers that are fully featured and portable. They do the same thing as layer 0, practically speaking, where the user will use the layer 1 to access the hardware, but they typically have many more features than a layer 0 driver does and are much fewer rough edges. They're also much safer. Layer 0 often has risks of not making sure the user doesn't do something they're not supposed to, whereas higher level drivers often do that. And the layer 2 drivers are provided by the operating system in order to convert a layer 1 driver to an operating system specific interface. So bare metal standalone designs will use layer 0 or layer 1 drivers, and then an operating system may use a layer 2 driver. In fact, one cool thing about these layers, and the reason why the layer representation is accurate, is that usually the layer 1 driver will include the layer 0 driver, and the layer 1 driver will use the layer 0 driver functions for its own functions. So the layer 1 driver is in many ways a more elegant expansion of layer 0. Layer 2 is a more OS specific driver that typically will not be provided as a part of the IP, but will rather be provided by the operating system. This figure here shows a standalone which is a bare metal system, where the user will access the layer 1 and the layer 0 drivers. These drivers can both be used at the same time. They are not exclusive. Sometimes it makes more sense to use the layer 0. Sometimes it makes more sense to use the layer 1. These are both provided by Xilinx because they are general to the SoC hardware and are not operating system specific, whereas layer 2 is operating system specific. And therefore, the manufacturer of the operating system needs to provide, or in some cases, the open source project. Layer 0 and layer 1 drivers are included in the board support package or OS and will typically be included as a part of the Vitis project when designing an application. So just as a casual example, recently I was designing a system that used an I2C interface in the programmable logic. And when I was working on the software in Vitis, Vitis included the drivers, both the layer 1 and the layer 0 drivers for the I2C. There are distinct naming schemes for this too, so you can tell which layer a driver is. Drivers are meant to bridge the gap between simple, easy-to-use functions and complex hardware register sets where the user needs to manage every bit that they're writing to the register. These device drivers have API calls, which are similar between different drivers. So the process for using an I2C driver will look very similar to the process for using a SPI driver. Obviously, the functions will be different, but the naming scheme and such will be similar. So it's pretty easy to understand similar functions that are meant to be used across different drivers. These similarities make designing with these drivers very consistent, making it faster to develop and debug. There is a header file called xbasictypes.h, which is meant to ensure that the drivers being used will always be correct for the platform and will provide the source code. Typically, a peripheral only has one device driver. You wouldn't usually have two different drivers for a single IP. It is possible to modify the driver yourself if you want to. One key difference between layer 1 and layer 0 drivers is that layer 0 drivers are tied to a single instance, where the layer 0 driver will, running this command, will run the command on a single instance of the hardware. So a single instance of the IP. This can become a problem if you have multiple versions of this IP in the project. In that case, layer 1 drivers make things much simpler because the layer 1 driver contains a data structure that will track multiple instances of one type of hardware. We'll talk in a bit about how drivers interact with multiple instances of hardware. Some characteristics of layer 0 drivers, which are both advantages or disadvantages at different times. They have a small memory footprint. They're very simple and straightforward. They have almost no error checking. So the user will perform a write and the driver won't do anything to verify whether this write makes sense or not. They only support basic device features. They won't support some of the more sophisticated options for different IPs. Same for device configuration parameters. They don't inherently support multiple instances, which is important, again, if you have several copies of the same type of IP. So if your processor is connected to multiple FIFOs or multiple block RAMs, then a layer 0 driver will start to have problems if the user doesn't handle them. They support only pulled I/O, no interrupts or blocking. This is a significant limitation sometimes. And they're always labeled with an _L or an _HW. Layer 1 drivers are higher level and are available as macros and functions. They will fully utilize all device features and support interrupts and more complex operation. They can be a little less beginner friendly sometimes because everything looks more complicated, and that can be intimidating sometimes. But they also have a lot of advantages. These layer 1 device drivers are still highly portable. Layer 0 is as well, due to the abstraction of these APIs. They will support device configuration parameters in multiple instances inherently. The user does not need to address these issues. Support pulled and interrupt modes, as well as blocking and non-blocking calls, and have large buffers. Because of this, they take up a lot of space. So there can be downsides of using a layer 1 device driver in a very limited resource system. Layer 0 drivers have the advantage of being small, simple, and quick, whereas they have the disadvantage of lacking more sophisticated functionality. Whereas layer 1 drivers have the advantage of having interrupt support and supporting multiple instances, with the downside of taking up a lot of space and sometimes being trickier to use. As examples of layer 0 and layer 1, we see here the layer 0 function for UARTs are send byte and receive byte. These are very simple to use. They take data, they take a length, they take an address, and they just send it. It's very straightforward. However, they don't really do much sophisticated. On layer 1, you have this XUART PS send, which if you would examine it, looks much more complicated. Under the hood, the UARTPS send function uses the XUARTPS send byte as a part, but it also performs a lot of validation and configuration of different things. So if layer 1's better, why would you use layer 0? Here's a simple answer. What are you trying to do here? If you're trying to do something very simple and straightforward where there aren't sophisticated concerns, there are not multiple instances, there's only one UART, a layer 0 tends to be much better because it's significantly easier to use and uses fewer of your system resources. If a lot of data is being sent, however, then the user is going to need some of the features of layer 1 drivers, such as having a memory buffer to store the large blocks of data instead of having to just read all the data one byte at a time, as well as allowing interrupts and other elements where having the extra functionality might be useful. So rule of thumb, if it's simple and there's only one of them, use a layer 0 driver. If it's more complex and there are multiple instances of the IP, layer 1 is usually the answer. But all of these drivers are provided and available though, and will be included in the Vitis project. The device driver needs a few things to work. It needs to know which registers to set or clear, because every driver will need the ability to reset or set different registers in order to function at all. Needs to know which drivers to change as per conditions changing. When it wants to perform a different operation, what registers need to change. The driver needs to know where to read and write the data. The user should not be, one of the points of the driver is that the user does not have to provide a direct memory address. The user can provide some sort of general function, and the driver will automatically understand where in the hardware design the device is. And the driver needs to know when to perform these operations. Drivers need to be aware of how to drive the peripheral, and the driver needs to understand things like which register resets the peripheral, which register stores the right data for this peripheral, and things like that. Needs to have minimal impact on system performance in order to not jeopardize the overall functionality, and it has to be portable as part of the description of these drivers. Some examples of information a driver needs in order to function. An LCD controller has a requirement that the LCD must be allowed to settle for some time before being rewritten. This is a requirement of the hardware that the driver needs to be aware of in order to prevent the software from just constantly writing. Data structures, multi-threading, and re-entrant capabilities can be affected by elements of the hardware design. And in general, understanding the hardware is critical in order for the driver to work right. One reason to include the device driver is to provide services for future software applications. When you design your drivers, you want to accommodate things that you may not need to do now, but you will need to do. And in order to do this, you need to understand the hardware capabilities and limitations. Two major concepts here are multiple instances and re-entrant drivers. We talked about multiple instances a little earlier. A multiple instance is a case where you have two copies of the same IP or hardware device in the design. This means that you can't just have one I2C driver without clarification of which one the driver is meant for. There are two approaches that can be used here, which are copying the code twice. So I'll have IP1 driver and IP2 driver that are just two copies of the same thing. Everybody who's designed software has probably experienced why this is not a great idea for a few different reasons. One of which is that if you change the driver, then you need to make sure you change all the copies of it. The advantage is the devices exist on independent drivers that have no correlation. So it's kind of the quick and dirty method. The other option is combine multiple functionalities into one code base. where you have a single driver that controls two objects. You have to be careful with this because if you have two different devices for which the driver is being called at the same time, there are concurrency issues and possibly unpredictable behavior. The real solution to multiple devices is reentrant drivers. For a reentrant driver, the same driver can be used to allow multiple concurrent invocations without interference. This driver can be called on two different devices at the same time without any issues. There are some requirements for this. In order to do this, the shared variables have to be atomically read written, which means that nothing can interrupt this read or write. Because if the read or write can be interrupted and two different devices try to access it, all sorts of things can happen. Being atomic allows for everything to be more robust and consistent, and it allows the user to store the code for multiple device drivers in the same code base without worrying that both will access the driver at the same time. Every IP processor and peripheral in the IP catalog comes with a driver that is provided as part of the Vitis unified software platform. These are used for the standalone library. This only applies to the IPs that are in these catalogs by default. As part of designing a custom IP, it becomes the user's job to write a driver for it to allow their software to access it. Whether that is typically part of a software task as a part of the project. The drivers that are provided for the built-in IPs are meant for maximum portability to allow the user to port between different hardware platforms potentially and different operating systems easily, allow maximum configurability of the programmable logic, and to support as many use cases as possible. One of the goals of these drivers is to be able to port very quickly from one platform to another. Another element of this are the configurability, the programmable logic, which means that the more you can customize the driver without changing the driver itself, the more control the user has over the hardware, and the more variations of the hardware the user can support. This capability is provided by allowing the user to change different parameters of the driver, which then flow down to the way the driver interacts with the hardware. There are also standards to the built-in drivers. There are coding standards, so they all should look the same. And they have a consistent API that looks very similar between drivers for different devices. In summary, the device driver is software that simplifies accessing peripherals and is really the tool by which your hardware and software interact with each other. These drivers can provide layer 0 or layer 1 surfaces, basic services like reads and writes or more sophisticated ones. And layer 2 services are provided by the OS manufacturer. Again, layer 0 services are best, layer 0 drivers are best to be used in simple use cases. And layer 1 are meant to be used for more sophisticated capability where resources may not be as much of a concern. So in summary, we discussed driving the Vitis tool and how Vitis projects are structured to design software, and the drivers that enable software designed in Vitis to interact with the hardware that was designed in Vivado. As the final subject for today, we are going to discuss the Versal adaptive SoC devices. The Versal devices are the comparatively new family that have a number of major changes from previous generations and specialized capabilities that may be of interest for designs. We're going to discuss what the architecture looks like at a high level and what makes a Versal device, identify different types of engines that are included as a part of the Versal adaptive SoC architecture, and talk about the network on chip NoC and memory hierarchy that are really what's special about these Versal devices. The architecture of a Versal device contains a number of different engine types that can be used for different things. Scalar engines are the traditional equivalent to the processing systems in the older Zincs, MP socks, and include ARM Cortex A72 and ARM Cortex R5 that control the adaptive sock and provide edge compute capabilities. These are your processors similar to older generations. Adaptable engines provide bit-level compute solutions that you're used to. These are comparable to the programmable logic and allow the user to leverage proven IP or your company's custom designs in RTL files or other methods. Finally, we have intelligent engines. These AI adaptable intelligence engines. These can be used for AI compute as well as diverse DSP applications and are very good for doing certain types of math that we'll discuss. One of the most special aspects of these Versal devices are the NoC, the programmable network on chip. As opposed to older generations where you had specified interconnects between a processing system and the programmable logic, and different interfaces were hard connected to the programmable logic or the processing system. Over here in these Versals, we have a programmable network on chip that allows every element of the system to interact with these different interfaces. So using the NoC, the PCIe, for example, can be accessed via programmable logic resources or the scalar processor resources, all through the same NoC. As far as these interfaces go, there are a few interesting ones in the Versal devices: PCIe Gen 4 and Gen 5. There are DDR memory controllers connected to the NoC that can be used by both the scalar engines, the adaptable engines, as well as the AI engines. And there are a number of different types of programmable I/O that differ from previous generations. The scalar engines, you execute complex algorithms and decision-making for autonomous systems, provide safety processing and redundancy for critical applications, and manage the entire platforms. These processors are used for loading each aspect of the adaptive SoC device and monitoring system status. If there's a need to extend the processing system capabilities of the system, you can also use microblaze processors in the programmable logic, which can be run together with these scalar engines in the processing system. These contain an applications processing unit, an A72, and a real-time processing unit, the R5. Very similar to the Zinc MP SoC processing system, but it has an ARM Cortex A72 instead of the A53. There is also the platform management controller as well. The APU is an ARM Cortex A72 dual-core processor, which contains a system memory management unit, a cache coherent interconnect, and different interface channels and system peripherals. These include some different useful features: 1.7 gigahertz speed. It's an ARM v8 architecture, and the APU starts up very quickly, and you don't need a bit stream for it. These processors can run different applications using both Linux and bare metal, as we discussed in the Vitis section. The RPU, the real-time processing unit, is based on an ARM Cortex R5F. The advantages of the RPU contain functional safety. This is not new. It existed on the R5 and the MP SoC, but they were always making improvements. The R5F can operate in split mode, where it's optimized for either performance or safety. And there are low latency determinism and real-time control, which are critical for real-time applications. So there are different options in the list of scalar engines that can be used for different types of applications, both for real-time as well as for more typical applications. The last part of the scalar engine section of the device is the platform management controller. In the UltraScale Plus, this used to be called the PMU. Now it's called the Platform Management Controller, or PMC. Its primary functions include controlling the device configuration, security and device integrity, testing and debugging, and system monitoring. The device configuration features include initializing the device after a system reset or on power on, controlling how boot and configuration is supposed to occur from a supported boot device, and configuring the adaptable engines using the configuration frame interface, or CFI. The PMC also provides security and device integrity functionality, such as encryption and decryption, authentication, and key management. The PMC controls test and debug infrastructure, many of which are unique to the Versal family of devices, and supports boundary scan and ARM core site trace and debug. Finally, there's a system monitor that monitors the system activity, responds to security and functional safety events, releases the processing system from reset, and provides system power and error management resources. So in summary, the scalar engines contain the ARM A52 applications processor applications processing unit for general applications, the R5F real-time processor for real-time applications, as well as the PMC platform management controller to manage the system as a whole, things like boot and configuration, and as well as different types of debug. The next major element of the Versal device are the adaptable engines, which are the programmable logic. These are the traditional FPGAs that you think of when you think of Xilinx. There are millions of system logic cells that can be used for any workload, which you can reconfigure on the fly. These are configurable to support designer needs, including parallel architectures, pipelined architectures, and hybrid architectures. There is a wide variety of memory elements in the system logic cell region, such as LUTRAM, BlockRAM, UltraRAM, and memory interfaces. One of the major elements of the programmable logic is the CLB, the configurable logic block. These include logic and lookup tables. These can be configured into different combinations and can create special purpose functions, processing units, and other interfaces. These CLBs exist in different forms throughout the different families of devices, from the 7000 series devices to the UltraScale Plus devices to the Versal devices, but every generation there are improvements made to these. In the case of the Versal devices, the CLB contains 32 LUTs and 64 slice flip-flops. There are carry logic and multiplexers that are in some ways more extensive than previous generations, different control signal configurations in order to optimize your resource usage. And half the LUTs can be combined to form LUTRAM and shift registers to provide more design flexibility. There are dedicated interconnect paths between each combinational logic block. The Versal architecture has complex and simple clocking requirements that are managed using global clocks, which are distributed on clock routing and clock distribution resources. Every device family has a unique clocking configuration that manages the clocking resources and timing throughout the device. The global clocking network in the Versal architecture is largely similar to the UltraScale family structure. It's a bidirectional segmented network of clock spines that support many independent clock networks and allow the same structure to be used for low skew or low propagation clocks. The core is divided into columns and rows arranged in tiles. In this example, the clock routing and distribution tracks drive horizontally, whereas the vertical routing and distribution tracks drive vertically into the clock regions. The clock management functions, which include MMCMs, clock managers, as well as XPLLs and DPLLs, provide clock frequency synthesis, deskew, and jitter filtering. The clock input pins on the Versal architecture drive these XPLLs, BuffGs, DPLLs, and MMCMs. There are several different types of I/O in Versal adaptive SoCs. There is the high performance XP and the high density I/O HD I/O. The XPIO includes dedicated logic to support high-speed interfaces with voltage ranges between 1 and 1.5 volts. These XPIO are grouped into 54 pin banks with supporting resources for both high performance and low speed interfaces. The XPIO can use the XPHY to align, serialize, and deserialize the data stream. The HDIO supports interfaces with voltages ranging from 1.8 to 3.3 volts. So the I/O pin that should be selected depends on the voltage level of the resource. Low voltage resources with high performance are ideal for the XPIO. Higher voltage resources from 1.8 to 3P3, however, need to use the HDIO. There are no overlapping voltages or I/O standards between these two banks. Every voltage standard is going to specifically either need XPIO or HDIO. XPIO goes up to 1.5 and HDIO only starts at 1.8 volts. Each of these have interconnect logic to support low speed single data rate and double data rate interfaces and coarse data alignment. The I/O buffers support a wide range of single-ended and differential I/O standards, which again will depend on whether XPIO or HDIO. And processor peripherals can be routed to the multiplexed I/O pin or MIO pins. So some of this is similar to the I/O setup in the older UltraScale Plus devices, but the XPIO and HDIO setup are different. So in summary, the adaptable engines consist of the FPGA programmable logic. These adaptable engines include combinational logic resources and clocking resources, as well as different I/O standards that can be used to connect to different devices. Finally, we have the intelligent engines. AI is pretty common around these days. AI is being used for a lot of different functions. The adaptive SoC provides a wide range of neural networking capabilities. One example are the DSP engines, the digital signal processing engines. These are used for high precision floating point computation. They offload additional functions to the programmable logic for acceleration. One thing I want to highlight about these DSPs is that these DSPs are actually a part of the programmable logic. They are physically part of the adaptable, it's unique elements that are part of the adaptable engines. The other major element of the intelligent engines are the AI engines, the adaptive intelligence engines. These are built for high throughput and a power efficient structure. They're great for DSP as well as advanced signal processing applications. The digital signal processing engine combines high speed with a low size to provide high performance and system design flexibility. The DSP engines have DSP58 slices that are integrated into the PL. The DSP58 is new to the Versal architecture. It has more functionality than the DSPs in some of the older generations. Each DSP slice contains a 27 x 24-bit multiplier and a 58-bit accumulator. These compare to the old 27 by 18 multiplier and 48-bit accumulator in the old DSP48. The multiplier can be dynamically bypassed, and the two 58-bit inputs can feed a single instruction multiple data arithmetic unit. Or a logic unit can generate different logic functions on the two operands. By expanding the size of this DSP, this allows substantially more bandwidth through these DSPs for signal processing. The DSP58 supports modes such as fixed point, the end-8 dot product, single precision floating point, and 18 by 18 complex multiply. One of the most unique things about the Versal family of devices is the network on chip, or the NoC. The NoC is a massive bandwidth programmable network that abstracts away the hardware and connects the engines and hard IP together. and binds all of the elements of the Versal device. Unlike a typical NOC in an ASIC, it can be programmed for different data flows between high-speed I/O and engines. As a part of the configurable logic, the NOC is fully configurable. It also has the ability to prioritize between throughput, latency, and even bit width. The NOC can be customized to be optimized for different types of applications like that. Traditional routing in the adaptable engines is available to meet specific latency or determinism requirements. It's not just about getting the data from point A to point B. The NOC gives you the ability to compartmentalize the kernels that are created on the adaptable engines with easy entry and exit points to move data from I/O to different parts of the fabric without having to worry about complex floor planning. Since the NOC connects the entire device, the NOC gives the hardware logic the ability to connect directly to any interface on the device that's connected to the NOC. The NOC has hardened connectivity to the memory controllers and PCIe core without any place and route. So there's no place and route that occurs between the NOC and the hard resources, which enables communication immediately at boot because they do not need to be configured. The NOC makes it placing IPs and kernels easier. It allows the user to compartmentalize the kernels with easy entry and exit ports, the ability to connect any master in the device to any slave. The NOC is AXI4 based, so the connections between the NOC and all of the interfaces here are through AXI4 interfaces. And the NOC extends in both hardware and vertical device directions to the edge of the device. There are some unique aspects to the memory hierarchy in the Versal family of devices. For the adaptable engines, a rich mix of memory is available. At the bit level, LUTRAM is the fastest and most distributed memory available. It has by far the lowest latency. At a byte level, however, block RAM and UltraRAM are highly configurable for multi-kilobyte distributed memory. For the intelligent engines, there are some unique aspects that you would not have seen in earlier generations. Each single instruction multiple data processor has its own instruction memory and data array memory. And adjacent SIMD tiles can share multiple memory structures. So each one of these AI engine tiles can share memory with the other AI engine tile. There are also special accelerator RAM that can be used specifically to share across accelerator engines, as well as HBM in certain families. The Versal Adaptive SoC architecture provides the interconnect module for PCI Express operating in CCIX mode. It's a high bandwidth, scalable, and reliable serial interconnect building block solution for use with Versal Adaptive SoC devices. The main components of the CPM are the two integrated PCIe controllers and a cache coherency block. Xilinx offers two integrated PCI Express controllers in the Versal Adaptive SoC CPM, the PCIe 0 and PCIe 1 controllers. Both of these support CCIX capability. The integrated PCIe controllers operate as endpoints when they're used in CCIX mode. Typically, these PCIe controllers will be used in endpoint mode rather than as a root point. The cache coherency block specifies CPM cache and coherency architecture. The CCB is the CCIX gateway to on-chip and off-chip processing nodes and memory. The CCIX gateway capabilities are achieved by a combination of the CHIB and PCIe transport interconnect. The CPM also contains the necessary components to allow a logic accelerator to act as a CCIX compliant accelerator. The CPM connects to the transceiver's programmable logic and processing system to allow any of the processing system, programmable logic, or transceivers to interface with the PCIe system. The AI engines consist of a number of tiles that have multiple elements as a part of each tile. The AI engines really are a network of these tiles. Each AI engine tile has a scalar processor, a vector processor, and local memory that comes with a DMA data mover. These AI engines include an array of SIMD and very long instruction word processors, each of which have their own instruction or data memory. They're connected on a unique interconnect that's been built with massive bandwidth. This enables the different tiles to share resources. Often in an AI engine application, you will see the memory of different tiles being used along with a single AI engine processor. AI engines can provide up to 5 times higher compute density for vector-based algorithms, and these are provided within the system power and thermal profile by complementing the DSP58s. Not every Versal device is the same. There are a number of different Versal device families which can be more or less useful for different applications. Each one targets a specific use case. All of them include the processing system as the scalar engines, programmable logic, and the network on chip, along with different memory controllers, transceivers, and hierarchical memory. The amount may vary across families, but they all have some. What may not be included in every family are AI engines and HBM. These are more features of specific families. The first family to talk about is the Versal Prime family. These are mid-range devices that are optimized for connectivity. This is a part that can be used for different things. But really, this is the part that's most similar to the older family of zinc MP stocks and similar. So this device is the closest to the older generations, although it's still very unique because of the knock and changes to the Versal architecture. However, if you're looking for something that can do what some of the MP stocks and RF stocks might do, but better, sometimes this might be your family. The AI Core series contains the adaptable intelligent engines. These parts are great for machine learning, DSP, and other artificial intelligence class issues. There are different parts in the AI Core series that have differing amounts of DSP, AI engines, and hierarchical memory. And the designers can pick the best part in the AI Core series. This series offers the highest throughput for low latency inference and is optimized for cloud, networking, and autonomous applications. The AI Edge series is the other family of Versal devices that has AI engines. These are used for edge applications, real-time issues like applications like automated driving or predictive systems. This family provides more than 4 times AI performance per watt versus the leading GPU solution. There are multiple parts in this family that can be chosen for different applications. The HBM series is unique due to the HBM in the name. HBM is high bandwidth memory that offers up to 8 times the bandwidth over DDR5 components at lower power. The HBM series integrates an extensive set of networked multi-terabit connectivity cores and 112 gigabit transceivers adaptable to emerging network protocols and modules. While doubling the transceiver speed, every layer of the network infrastructure is secured with encryption engines. This series offers twice the logic density of the previous generation HBM solution to maximize performance for constantly evolving algorithms and protocols. Finally, we have the Premium series, which are high-end, high-bandwidth devices with high-density logic. Really, this series has a lot. It's the AI Core series, but it has a lot more of everything. So these are the high-end ones, but they do not have AI engines. In summary, the adaptive SoC includes 3 major categories of devices: scalar engines, such as processors, adaptable engines, and programmable logic, intelligent engines, and the AI engines and DSP engines, and provide programmable network on chip connectivity to allow flexibility to access all the different resources in the device. Next, we'll just finally discuss the Versal Adaptive Sock design tool flow. We'll talk about, so a lot of this is going to cover things that we've addressed in terms of Vivado and Vitis, just in the context of Versal devices. We'll describe the Vivado and Vitis tool flow for Versal devices and how application acceleration works. The adaptive SoC provides the capabilities of heterogeneous processing CPUs, FPGAs, and intelligent engines within a single platform. These are all connected to each other by a network on chip. This single platform constitutes three major types of engines: the adaptive engines, the acceleration engines, and the hardware platform. Different tools have to be used due to all the different capabilities of the elements of a Versal device design. Vivado and Vitis can be used for the programmable logic and associated resources. The Vivado design suite is used for the manual hardware design in a traditional way, and the high-level synthesis tools in Vitis are used for hardware system creation. The tools like BRAM and DSPs and similar IP that you might be used to in the past will typically be done using either Vivado or Vitis. One thing unique about Versal devices in Vivado is that IP integrator is used to connect the NOC to various blocks. Whenever an IP or a processor is connected to the NOC, a NOC IP is placed in the IP integrator design. Another thing is that the CIPS, control interconnects and processing system, replaces the old processing system IP from previous generations. One additional feature in the Versal adaptive SOCs is the adaptable AI intelligent engines. These require a special set of tools to use. For the scalar processors, similar to previous generations, the Vitis ID will be used, which supports ARM RISC processors and enables bootable image creation. There are two major categories of Versal devices, besides some of the more specific ones. There are the Versal Prime and Premium series, and there are the AI Core series. There are two ways to design hardware with a Versal device. One is the traditional programmable logic only flow. When designing with this flow, the AI engines cannot be used, which is why this flow is not mentioned as an option for the AI Core. The AI engines cannot be used this way. This process involves simply using Vivado, writing the code or building the block design for hardware design, and generating the output, similar to a traditional FPGA. The other flow is, now, even for an embedded design, the traditional flow can be used as well. Software can still use the XSA file that we described earlier for a Versal device, just the AI engines cannot be used for this. The other option flows are the platform-based flow, where a general hardware platform is created. Sometimes this is done via a pre-existing Xilinx platform, such as with the Alveos, and sometimes it's custom platform designed for specific hardware. So for a PL-only system, this is a hardware-only design. This is created using the traditional Vivado design suite, which generates a PDI. So the programming files look a little different for Versal devices. They're a PDI format, which contain a programmable logic RTL implementation, similar again to the traditional FPGA flow. These operate autonomously without using the other components of the Versal device, and the programming is handled by the platform management controller above. An embedded system comprises of an embedded processor, acceleration logic that's built into the traditional programmable logic. This embedded system consists of an A72 and an R5, and the use model for a traditional embedded design would be whether it's a sophisticated embedded software stack or a simple bare metal stack. In the traditional flow, no platform is used. The hardware can be designed in Vivado, creating a XSA, and then the software can be designed in Vitis, similar to the way we described in the Vitis section. In this case, the Vitis tools cannot change the programmable logic. The Vitis tools accept a fixed definition of the programmable logic and don't make any changes to them. The other flow, though, is the platform-based flow. In the case of a platform flow, the hardware design is developed into two elements, a platform and a processing subsystem. The platform contains the core Versal IP blocks, including the CIPS, the NOC, AI engine, and clocking wizard, as well as board interface IP blocks. Since these are physical blocks, Vitis cannot change any of those. However, for the application-specific parts of the system, the processing subsystem is designed to include them. An embedded AI engine system contains an embedded processor as well as acceleration logic, such as a traditional programmable logic and AI engines. On a Versal adaptive SoC, this includes the embedded processing system, as well as the hardware and the programmable logic and the platform-based design flow. There are also pre-built platforms, as shown. For typically, the pre-built platforms will be used during the early stages of a design, where perhaps the hardware design that the user is designing has not been completed yet. So the platform can be used as a platform to develop software while the hardware platform is still in development. Xilinx recommends parallel development, where the application team works on the software subsystem, which includes the accelerators that are part of that, and the platform team works on the custom platform. Using a pre-built platform can substantially streamline the system integration process by developing the software subsystem based on a pre-existing platform and not having to wait behind the hardware engineers finishing to developing the platform. All of this is done in the Vitis unified software platform. This platform supports a number of open standards and is very useful for programming the Versal adaptive SoCs. You can compile software and AI code on heterogeneous platforms. This tool combines all the elements of Xilinx software development into one unified environment. This includes the software flow, the software development flow, as well as the Vitis application acceleration development flow. This includes the traditional SDK, more recently Vitis software development flow, as well as using HLS to develop kernels, which can be integrated into the hardware via the acceleration development flow. The Vitis development kit supports running software applications on an embedded processor system running Linux, such as UltraScale Plus MPSoC. The Vitis development kit can also use the OpenCL API or the Xilinx runtime to schedule hardware kernels and control data movement. Using these tools, Vitis can actually change the hardware that is running on the device. The Vitis environment also supports debugging and profiling the applications and can be used in both the GUI and command line. This is based on Eclipse. The Vitis application development flow provides a framework for developing and delivering accelerated applications using standard programming languages. For FPGA-based acceleration, a software application can be built using an API such as OpenCL to run hardware kernels on accelerator cards. The Vitis Unified Software Platform is an integrated development environment that for the development of embedded applications targeting these processors. Vitis can target acceleration hardware platforms, such as all the different families of Zinc, as well as the Versal devices. Vitis Runtime provides an API for your host program to connect with the target platforms and handles transactions between your host program and accelerated kernels. These libraries provide performance-optimized FPGA acceleration with minimal code changes and without the need to re-implement your algorithms to harness the benefits of adaptive computing. There are pre-existing libraries that can be used to aid your development, such as statistics or DSP, where there are built-in functions that can be used to create the accelerators to be added to the platform. The philosophy of the Versal system is based on a divide and conquer approach, where the system can be broken down into multiple discrete elements that need to be built. A subsystem is a combination of processor, system firmware, programmable logic kernels, and potentially an AI engine graph application. A subsystem forms a standalone entity performing a well-defined function under the supervision of the processing system. In this example, see subsystem 1, where there is an AI engine graph and HLS kernels and the programmable logic, and they are connected through the data mover kernels and firmware in the processing system. So the processor system application uses the firmware to access the programmable logic kernels and the AI engine graph, and the other subsystems do not have AI engines. Only one subsystem at a time can have an AI engine. A platform insulates developers from the low-level details and lets them focus on the high-level application development, whether that be for software or hardware. The hardware platform is an IP integrator block design that contains the essential IPs and can be exported using Write HW platform. There are also configuration settings that can be configured in Vivado for it. The software platform is usually generated using the Pedal Linux tool suite to create the first stage bootloader, device tree drivers, and operating system. This can sometimes be done in Vitis as well. Compute acceleration is the acceleration of computations performed on the scalar engines using specialized accelerator hardware. The accelerators are the hardware and the programmable logic that the software in the scalar engines uses to optimize performance. This can be something simple like using the processor's math coprocessor in order to supplement the programmable logic, or more sophisticated applications. These processors and accelerators are tightly coupled in memory hierarchies in the NOC, using the network on chip to move data between each of these adaptive and scalar engines as efficiently as possible. As you can see, a Versal device can include a lot of different elements. There are programmable logic kernels, which can be done using programmable logic or RTL kernels. There is a hardware platform to be imported into Vitis, as well as a software platform for your software applications. There are the AI engine tools for the kernels and graph, as well as a simulator. And then there are the programming system interfaces such as Xilinx Runtime and the Graph API to allow the processor to access the hardware. For the processing system, Pedal Linux develops the Linux image, and the Vitis tool is used for the embedded software development flow. The applications developed in Vitis will then be integrated into the Pedal Linux image to run on the board. For the programmable logic, IP integrator is used to create the block design, and Vitis HLS is used to create custom IPs. Additionally, RTL kernels can be developed as well. Accelerator kernels can be developed in both C or C++, as well as traditional HDLs. The AI engines have a special compilation process, which is done through the Vitis platform. Vitis environment is your method for binding all of these together and allowing them all to interact with each other. The AI engine tools are the tools that are used to compile the AI engine designs in order to, as we mentioned earlier, each AI engine has a processor on it. the AI engine tools compile the software to run on that processor. User code for the processor is compiled in order to run on the AI engine. These can be reconfigured. QEMU allows for emulating the hardware of the device, which sometimes when hardware is not available, being able to emulate the software system booting up is important. Another method to create kernels is Vitis Model Composer, which enables rapid design exploration within MATLAB and Simulink, and allows you to turn your MATLAB algorithms into hardware code to run on the device. You can use MATLAB or Simulink to go through the algorithms using high-level performance optimized blocks and use MATLAB simulations to validate your functionality. Model Composer will then turn that into production quality hardware code, which can be implemented on the device. These can be used to create the accelerator kernels as well. Model Composer has superseded System Generator for DSP. It has all the functionality and more. Model Composer can be used to target AI engines as well. And you can use your MATLAB code to write code for the AI engines. The most recent version of the user guide describes the process for doing this. Finally, we'll take a look at the compilation process for a full-on Vitis design that has all these different elements in it. For the software development, the GCC or G++ compiler are used to compile the C or C++ source files targeting the processor. This generated executable uses the Xilinx runtime library to communicate to the low-level hardware. AI engines have their own compiler, the AI engine compiler. This is used to compile the C or C++ source files that are specifically targeted to run on these AI engines. These compilers generate output in the form of a library file, libadf.a, which contains both the ELF executable file and CDO configuration data files, as well as tool-specific data and metadata for hardware and hardware emulation flows. To create a loadable image binary, this data must be combined with PL-based configuration data, bootloaders, and other binaries. The Vitis packager performs this function, combining the information from the library and the Vitis XSA Xilinx support archive. Then for acceleration development, the kernel source is compiled using Vitis HLS and then linked to create a complete design on the PL. This generates an XCL bin, the combined bit stream with the platform and the kernels, or the adaptive sock DSA that can be used to program the PL. Let's look at what a kernel is. We've been talking a lot about accelerators and kernels, which to a large extent are interchangeable terms. An AI engine kernel is a C++ program written using specialized intrinsic calls that target the very long instruction word vector and scalar processors. This kernel code is compiled using the AI engine compiler included in the Vitis integrated design environment. The AI engine compiler compiles the kernels to create an ELF file that will run on the processor on the AI engine using the memory on that AI engine. AI engines can be performed one kernel at a time or using different AI kernels and tiles. In summary, as a part of the Versal device family, Xilinx went out of their way to support all types of developers to facilitate hardware design using Vivado, software design using Vitis, and AI machine learning developers using the Vitis AI tools. And the Vitis Unified Software Platform is a platform for performing software development and compiling all these different things. You've got to compile your accelerators, you've got to compile your software, you've got to compile your AI engine code, you have to build, there's a lot involved. And the Vitis Unified Software Platform facilitates doing all that. And each compute domain on the system has specialized development tools. All right, so as planned, we're going to break for lunch now. And we'll continue the second part of this workshop with the hands-on demos at 1:15.
All right, everyone. So we'll take a break. It's 1:15 Eastern time that we'll be back. That's 1 hour from right now. So please have a moment to go grab some coffee or some food, and then we'll see you in 1 hour. I've dropped some links into the chat panel for some of the classes that relate to this material. And I also did want to call out that we are using slides that still say Xilinx. Xilinx was purchased by AMD. We do tend to refer to them as AMD Xilinx for clarity purposes, but AMD is now the owner of Xilinx. So do check out our chat panel for some of the related classes, and we'll see you guys back here in 1 hour. All right, everyone, welcome back. We're going to get started in just a second. I did want to mention right before we went to break, Nathaniel was talking about acceleration, and I just wanted to talk about the fact that that also relates to not to just what he was talking about, but also to the Kriya Psalm, and that Nathaniel is actually going to be teaching a webinar in November on the Kriya Psalm. So if you're interested in signing up for that, it's another no-cost event, and you can learn more about the Kriya Psalm and acceleration with it. So I will drop the link into the chat panel, and then you guys can check it out. So without further ado, Nathaniel, I'm going to kick it back over to you.
Right. Hello, I would just want to add to what Sharon's saying in context of what we've been discussing. I do just want to show off there's a user guide for platform creation and acceleration over here. UG, I think the full one is UG 1605. That provides a lot of useful information with regard to Versal platforms in general and Kriya as well as everything else. So for the next stage of this workshop, we're going to do a few hands-on demos of what building a Vivado project looks like. We'll start off by making a basic Vivado project in project mode. After that, we'll show using Vitis to develop a software platform and building a standalone bare metal software application in Vitis. We'll then, at the end, show how you can combine those skills into designing for a Versal platform. If we do have time, we'll spend a little time showing off some of how non-project mode works. But time may constrain us from going into non-project mode. So without further ado, let us begin the Vivado demo. So we are going to create a project in Vivado first. The easiest way to do this is to start Vivado using the icon on Windows or Linux. You can also start Vivado from the command line if you'd prefer. So we'll start by creating a project. Let's rename this project. The project will demonstrate blinking an LED through a UART. Oh, right, and we need to specify where this project will be. Sorry, there. And we need to specify the directory for the project, which will be the VHDL directory using the Kintex UltraScale Plus board. As you can see here, there are a variety of different project types. Just would like to highlight IO planning project is used for high-level IO planning of your device, where your design is not finished yet, but you need to figure out what to put on your circuit board and similar applications. Imported project imports an ISE project. An example project will you create a project from a number of templates. This can be very useful. I'm not going to actually create an example project, but I'll click through here just to show off some of the example projects. As you can see, there's a wide array of example projects that can show you what a project using a Versal CPM debug over PCIe setup looks like. These are great implementation examples for you to start working on your design based on. Obviously, you'll need to customize, but there are extensive resources for utilizing the different elements of a Versal or UltraScale Plus device. But for now, we're going to create our own project. Since we are going to specify our own sources, see this extensible Vitis platform option. We're not doing hardware acceleration. If we were doing hardware acceleration, then I would check this box, but we are not for this lab. The next thing we need to do is, since I have an existing project, I need to add the source files. So, and that is for this lab, the source files are here. I did not necessarily mean to add that as was. And since we're doing the VHDL version of this project, right, let's just double check. Are there VHDL files? Yes, there are VHDL files that are not selected. Right, all the VHDL files selected. Yes, and we will also need, so we'll add all the VHDL files here. As you can see, all these VHDL files are added. We are also going to need, next we're going to add our constraints files. Since we're not doing the Versal version of this, we're going to add the regular one. Next, we want to select the target port. The easiest thing to do here is to go to the boards. Every Vivado install has a number of boards attached to it. So for this, we're using a KCU 105. So we need to find the KCU 105. This is here. Sometimes cards have companion cards that can get added, but that's a bit of a more involved topic. And here we have our project, which is created with 14 source files and a Kintex UltraScale KCU 105. While this waits, I see a question in the chat. If using a device with a SoC but no AI engine, would the Vitis extensible checkbox need to be checked? That depends. For a traditional embedded design, you would not need to check the extensible checkbox. What I mean by traditional is that a design where you do the fixed hardware platform in Vivado, the software platform in Vitis, and you put it together, you do not need to check the box. The case where you need to check the box is when you're working with an accelerator, when you're doing this flow where Vitis is going to put the accelerator kernels into the platform, that's when it needs to be extensible. The most common use case for this would be an AI engine, because an AI engine is the use case that requires this. In every other case, it's going to be optional. This is true even if you're using a Kria. Kria is also compatible with both flows as well, if you choose to use them. Anyway, so let's make sure, do we have all the files we need? It looks like it. This question mark box, by the way, will show me any missing sources, and it's not showing any, so that's a good sign. No messages either. Now, that should be all of the design files. If we check out the dashboard, we can see a few things about the design. We can see the target language is Verilog, which doesn't look correct for what I'm doing, so let me change that. Change it to VHDL. There are other useful settings here as well you can look at when they're relevant. I could change my part here. If I want to move this to a different part, I can open this menu again from here. I do not, however, want to change that. The next thing is we're missing some simulation sources. So we don't have a test bench in here. So now we're going to add sources from inside a project. Since this is for simulation only, you cannot synthesize these files. We're going to use add or create simulation sources. Looks like I added the test bench files before already. So, but now the test bench files are in the wrong one. So here's what we're going to do. See how this is in the wrong source? It's in design sources. We're going to move to simulation sources because it's a simulation file. Additionally, these two are also simulation files. So we'll right click and we'll move to simulation sources. You can move files between file sets by just right clicking on it. It takes the hierarchy a second to update, but once it updates, we should see that design sources only has the design sources and all the simulation sources are in here. Now this is not the right top level. This is actually the test bench. So we're going to change this to set as top. The next thing we need to do is associate some files to another library. VHDL files, unlike Verilog files, must be associated to a certain project library. Right, this would have been easier to do earlier. All right, so all right, for now, we'll just go with this. Next, let's take a look at the file hierarchy. When we're looking at the design sources here, we see that we have a top level called URLED. That is our top level file. There are several sub-element instances of this particular design element in here, as well as a sub-element using of the UART-RX. And then in here, we have several sub-elements of the UART-RX that control the UART. This particular UART only goes in one direction. There's no transmit here. There's just an external element that will go and turn the LED on. Let's take a look at a few things about Vivado. So we have a project open. There are a number of things we can do with it. The traditional flow would be to run synthesis or run implementation. We're not going to do that right now due to time constraints, but this will generate an output product, which you can then run on the board. This will eventually generate a bit stream. One thing we discussed during this workshop was how you can configure implementation settings. So there are a few ways to do this. Every synthesis run has some settings applied to it. They're all in the global settings menu. There are a few elements to it. There is a strategy. There are a number of options to synthesize for different purposes to optimize size or performance. You can also configure quite a number of other things about synthesis in here. Something else you can do is create another synthesis run. So I have synth1 here. But I can also create a new run called synth2. In fact, I can create a new synthesis and implementation run. Since I want this one to be different, I'm going to change the run strategy here. Runtime optimized is a cool one because runtime optimized is designed to synthesize your design in as little runtime for your build as possible. It's not always great for your design performance or the resource management, but if you really need to get a synthesis done quickly, it's good to know that this exists. There are also two primary report strategies where you either generate the default reports or generate no reports. There are also options to use a user-defined report strategy sometimes. Here I have an implementation run. I can choose which synthesis netlist I should use. By having two synthesis runs, each run is going to store a separate netlist. Generally speaking, I would want to have my synthesis and implementation runs independent, but I can have an implementation run that goes back to the original synthesis run if I want. I could change parts. One good reason to have two runs would be to have one run for one part and another run for a different part. This gives you a lot of flexibility when you're designing. XEKU 035 I want. It's a very similar part to the 040, but not exactly the same. I can have different constraint sets, different file sets. I'll set this to runtime too, because if I set, there are a lot more implementation options as you see. So it gets a little harder to find things. And make active will make this the active run, but I'm not going to make it active right now. And you can configure how many processor cores this Vivado uses, among other things, if you'd like. I do not want to launch, so there's a checkbox somewhere back here for this. I'm going to check do not launch now because I don't want to launch this run. There's also a generate scripts only that will generate tickle scripts to launch this run if you'd like. So this will create the runs but not launch them. Right now, synth 1 is active. The active synth is the one that happens when I push this button. I can change this by right-clicking and selecting make active. So as we mentioned earlier in the workshop, having multiple run configurations allows the user to choose to have multiple convenient ways to build a design depending on what they need. A couple other things to note. Sometimes there'll be a compile order requirement on specific files. The tool's pretty good at doing this by itself, but sometimes you'll need to tell it what to do. As far as the horizontal toolbar goes, project summary opens up this window. So if I close it, I can open it back up like that. Can unselect all if everything's selected. Run will let you run the synthesis or implementation. I usually use a sidebar anyway, it's just more visible. And open will allow you to open different types of files. So you can open things as a text file if you want. So this will allow you to open a file without adding it to the project. Good for just examining things. Here we have the simulation tab. Whenever running a simulation, first it performs analysis and compilation. This is because I had something in the wrong library before. Since it's in the wrong library, the synthesis won't run. But if we go to simulation settings, there are a whole lot of useful settings in here. One setting I like to highlight when talking about synthesis settings is simulation settings, sorry, are how long is the simulation going to run? By default, when you select the run simulation button, it will run for 1 millisecond or 1 microsecond or 1,000 nanoseconds. If you want to change this to 1 second, it will take a lot longer for your simulation to run, but you can run it that way. There are some other useful settings here too. Since this implementation can also be pretty tightly controlled, one thing you can do is run your own tickle scripts as a combination. You can set up your text editor. You have a lot of flexibility with how Vivado looks if you want it. Vivado will syntax check for you. You can add your own IPs here. We cover all this in our Vivado bootcamp too in much more detail. It's just an overview of the different features of the tool. And yeah, you could change the parts in here. You can open the IP catalog in here if you want. This will add an IP to the project not as part of a block design. And you can create a block design like this. It takes a minute. Vivado is not always instantaneous, but then once you have a block design, you can add IPs. So if I wanted to add an MP sock, since this is a Kintex, I can add the Zinc Ultrascale MP sock in here. Oh, right. This board doesn't have an MP sock. Whoops. This is the Kintex. So if I want to add an MP sock, here's what I do. So let's go back to project properties. And we're going to change this to a platform that has a Zinc on it. So you see the IP catalog graded out because I don't have a Zinc. But let's say I change this to a Korea. Koreas have a Zinc. That's a good option for this. So now when I go back to, I'll open my old block design. Now when I try to put a Zinc in, now I have the Korea Zinc in here. Some IPs have to be added through a block design. There are other IPs that you can just add as individually to the project. So when you open the IP catalog from here, you can just add a generic. Let's go over look for FIFO. And this will create an additional FIFO in my hierarchy, but it won't be used anywhere. I have to use that myself. Now, the block design, the IP I created are now independent of the hierarchy because they're not used in the UART LED model. As a result, when I run synthesis here, anything that's not under the top module is not used. All right, so that was a quick overview of what designing in the Vivado tool looks like. The next thing we're going to discuss is software development in Vitis. And we're going to talk about how you drive the Vitis software development tool. So first off, we're going to open Vitis. This, as mentioned, takes a bit sometimes. So we need to choose a workspace. The workspace is going to be where Vitis stores all the files. By default, it will save all of your files and wherever the workspace was the last time you opened it. Right, I want to redo this. I can't save this here because these are new, but all right, I have this let me just open the project then. So here's the workspace. Since I opened a workspace that has a project in it, it should show all the projects in that workspace when it opens. So I have a number of different projects in here to look at. I imported these before, but let's just show it again. So we'll start a new, that's a new application. I want to start a new platform project. So the new platform project will be called AppDev2. The platform provides the hardware information and the software environment settings. This is what takes your hardware description file, your XSA, and allows you to build your software on it. The system project also has an app here. So the first thing I need to create a platform project is an XSA. There are a number of hardware description files that come by default installed with Vitis. For this one, we are going to use the VCK 190, which is one of the new Versal device development boards. Vivado will read in the specifications. Once it reads these in, I have a choice at this point. Sorry. So I specified the hardware description file. Now I need to specify what operating system is here. Standalone is used for bare metal applications that the processor is running directly. Linux will be used for Linux applications. Linux will generally be the operating system of choice for non-real-time operations. And for real-time OS, FreeRTOS Xilinx is usually used. Because this is a Versal device has a number of different processors. As we mentioned earlier, the VCK 190 has two different APUs. There's a dual core, it's a dual core A72. So you can run this on either core of the APU, as well as either core of the dual core R5. And you can also run things on the platform management controller or the PSM if you would like to. Typically, in most cases, you're going to find that you'll be running this on the standalone application on the default APU if there isn't a need for real time. Once I finish this, this is going to create a second platform system. So yeah, now I have two different, whenever this is done anyway, I'll have two different platforms. So if we look at our platforms, we'll see that my first platform is an MP-SOC that uses an A53 and has its own platform project in here that uses the UED ZCU 104. You can configure a number of the elements of this project if you want to. One thing I do here pretty often is modify BSP settings. I'm not actually going to change them for this project, but this will allow me to change the board support package. I can enable different drivers and resources. I can potentially choose different driver versions and compiler flags. And there are also options for other things. You can sometimes choose your UART and that sort of thing. Sometimes Vitis can be a little slow to the touch. I can also, when I replace my XSA, I can reload them using, I can reload my XSAs using this load BSP settings from file to reset my BSP to a new hardware description. This is one of the ways you can use to easily update your software project with new hardware information. So this is the platform project. It contains processor information, as well as different elements of the BSP, some make files, hardware description headers, and the hardware description files that are imported into Vitis. Clicking on platform.spr will open this tab here. So if I close this, I can reopen it with platform.spr. If I click on this platform.spr, which I think is open already, I'll see that there are some differences here. For one, this isn't really optional anymore. For two, I have the Versal options now as opposed to the MP-SOC options. Since this is a custom BSP, it doesn't have anything, since this is a pre-installed BSP, it doesn't have anything particularly interesting in it at this point. Whereas this one's a hardware platform, so it has all my custom hardware for my design in it. There are two different domains here. You can see the APU domain as well as the PMU domain. The other thing I have here is my system project. My system project consists of all my applications. In this case, I only have one application. I can open this by double-clicking the PRJ file. I can customize this. So for example, I can change this between platforms. So if I'm designing something that I may put on two different silicon chips, then I can use this to switch back and forth. In this case, because I used an out-of-the-box platform, it doesn't have everything I need for the app, so it warns me that I can't use this platform. But it's easy as that, just to switch platforms. You can also switch processor domains. In this case, it's not eligible to because of the nature of the application, but sometimes this will let you switch to a different one. And this hardware specification tab provides a lot of interesting things. This will give me the address map if I would like it of the hardware specification. Will give me a lot of information. This particular so yeah, you can change the OS version, you can change a number of other things. One thing I can change is where do I want my standard output to go? Normally this would be UART 0. I can connect it to a different UART, or for debug, I can connect it to core site. So what's in the application project here? What's in the application project are my sources. So this project's set up for an emulator. When the emulator is run, a lot of the hardware calls are not made. That's why the symbol's here. You can see how the device driver is used, the XGPIO write register. As well as different functions being called here. Since this project is built for two different boards, there is a compilation symbol here dictating, is this an MP-SOC or is this a Versal device? These symbols can be modified by right-clicking and going to edit C++ build settings over here. Should be able to see symbols. I think this is the wrong level to look at. I think I need to look down one. Here we go. If we look at the symbols on the ARM compiler, we see that I've defined this project as a DCU 104. I have specified that it's an ARM A53 and not the Versal's ARM A72, and I specified that I want to build this for emulation. So now that I'm not using this platform, let me get rid of this platform because this platform is not helpful for my project. Since this is permanent, because I just made this platform as an example, I'm going to delete it on disk. You can also delete it, remove this will remove it from the project, but not delete the files. It does say there are some warnings. Where are the warnings? Okay, none of these, since I have it set in emulator mode, that's why these warnings are here. So I have my hardware platform with my specifications, which I can change by going to the platform file. I can change a lot of things. Sorry, did not mean to open that. I can change a number of things over here. I have my system platform, which is the app system. I can add new projects here. I can also configure a few different things here. I can add a custom root file system, can add a custom kernel image. I can also, this is a big one, generate an SD card image for my project. It's not letting me in this particular one. And I can open the individual project over here. So now that that's done, let's build this. So just to show that slower, we right click and then select build project. Now that I've built the project, I don't have hardware with me right now, but I do want to emulate this. We're going to go to launch software emulator. If you look at the window in the bottom right here, this should, did I click it before finish building? Sorry, I think I'm frozen. There we go. So now that I've started the emulator, sometimes, as I said, this can be a bit laggy depending on your system. I'm on a virtual machine. That's the main reason it's taking a little while. Normally it doesn't lag like this. So these are just standard warnings that the emulator has on starting up sometimes. So now that we're here, I have this application as a stopwatch. I can start the application, stop, start, and reset. This is what would happen if you connected to the UART on an actual board with the processor running. While QEMU won't always show everything that might, while QEMU won't always show everything, it will usually give you a general picture of the things that might go wrong with your project. It's a good way of checking that your code compiles and does what you think it does. All right, so that's how you drive Vitis. You make a platform project by importing an XSA. Here's another good way to update your XSA. You can right-click on the platform and import a new one. You then create a new application project. So in this case, I already have a system project. Oh, right. So here's the problem, right? This is a single stream processor though. So my platform domain is a single processor. So I have two standalone projects running on a selected processor, so it will not let me do this. So if I wanted to create another application here, I would need to change the specification to something that allows me to have multiple applications on the processor. As we mentioned earlier in the workshop, a standalone processor without an OS can only run one application at a time. However, in a more complex system, I would be able to add another application here. So with that over with, let us move on to device drivers. There we go. Again, that's the virtual machine. Vitis is much faster than this normally. So Vitis is configured to always use the previous workspace. The reason why I don't want to check this box is because I typically want a different workspace whenever I'm starting again. So if I did this, it would always start from the same workspace. You can also restore other workspaces and go through all of your recent ones. So in this case, I want the app development standalone lab. So here we see pretty much the same platform as in the other one. It's still standalone on A53. It runs a similar stopwatch application. What we're trying to highlight here is how drivers are used. So the first thing we need to look at is, what am I driving? I am driving an AXI GPIO block. So what do I need for an AXI GPIO block? Well, I need information about the AXI GPIO. So I can see a few things. I can see that the GPIO has two I/O channels, and each I/O channel needs to be is a tri-state pin, which needs to be programmed to being an input or output. And the other thing I need here are, where are my registers? So here's a register for the AXI GPIO data. Here's a register to control the tri-state, whether the GPIO is an input or an output. So for example, if the GPIO is connected to an LED, then the GPIO needs to be an output. And this tri-state register needs to be set correctly. If it's connected to a button, then the GPIO is an input, and this needs to be configured correctly for that. If I read a little further, I can see which value is input and which value is output. I see 0 is an output, 0 and 1 is an input, so I can configure these correctly. Now, I could manually write, if I go back to the Vitis project, I could manually write in these values here. It wouldn't be a good idea, but I could. But because of the device driver, I don't need to. Because of the device driver, I can simply use the built-in function that comes with this in order to write the register. This function actually traces back to various Xilinx files I can find in the include if I want to. As part of the platform project, all relevant hardware drivers are in. When I go back to the platform project, I can in fact look into which driver is being used. If I look at the standalone BSP, takes a second. And I look at the GPIO, I can see a couple of things. I can see this documentation link. And I can import examples potentially. The documentation link will open the API for the driver. and give me a lot of information about the driver here. So I can see this is a level 1 driver that we were referring to before. When you see something like CFG initialize, that is a standard level 1 driver feature. Because it's a level 1 driver, it also contains data structures to handle multiple GPIOs. And every device has a number of examples which you can put in your workspace directly. So let me bring the low-level example in. And now I can look at this example while I'm writing my project. Once it imports anyway. Sometimes this can, again, that's the virtual machine. The virtual machine sometimes can be a little laggy. So now I have an example project in here. Since it's an example project, it's not a part of my existing system. I'm not going to run this anywhere. But it is a part of my platform. So now I have 2 different platforms on my A53. So let's look, what did this include? It included this, which is also available on GitHub, which shows me, okay, here's the driver file. Here is an xparameters.h, which is a part of my hardware file. And here are a number of useful constants. So this will show you how to use the GPIO. Here you can find all the headers that are required. It gets a little involved. So anyway, so I looked at my example project. Now I'm done with my example project and I'm doing revision control, so I'm just going to get rid of it. Since it's an example, I have no problem deleting this because I can always just download it again using the same process. So yeah, so the board support package tab will show you every hardware peripheral in here, as well as all of the associated drivers to it and some of the important documentation. So that was the BRAM. This will open up the block RAM control. And I can see here's how I use the block RAM. So Vitis integrates a lot of these capabilities. So when I go back to my original software system and I want to take a look at my top level file, I can see that I'm using this GPIO driver. So the GPIO driver contains all the information to say what these addresses are and which register to use. All right. For the next lab, we're going to put this all together and show how Vivado and Vitis are used together in the context of a Versal device design. So first we'll start with Vivado, because the first part of any Versal device project is to generate some sort of hardware platform. Once this opens, we will create a new project as per last time. This is going to be another RTL project. We're going to add the sources later. So this is also not an extensible project, even though there is absolutely a processing system on this board. Since we're not using acceleration for this, we're not going to check that box. Next, we need a VCK 190, the standard VCK 190 acceleration platform. Just some background, you can choose a part or a board. For a custom board, you'll often choose a part, but when you're working with one of the default evaluation boards, it's often easier to just use the boards tab to find it. Every board translates to a part. The silicon part on the VCK 190 is this XCVC 1902. Next thing we'll do is we will create a block design. When you're working with a processor or the CIPS, which is also a processor, block designs are not optional, they're mandatory. Because the IP cannot be added to the design any other way than an IP integrator. Next, we need to add the CIPS core, the control interfaces and processing system core. This can take a little while for large IPs. The SIPs is one of the most complex IPs, so it takes a second. We're not going to run block automation, but there are options for automating a number of things here. For one, you can automate using the SIPs with just a PL subsystem or a full system. You can apply the board preset if you have a board and not just a part. There are a couple options for debugs. There are a couple options for clocks and several DDR options, but we're not going to automate this for this project. Next, we're going to take a look at the customization options available for the CIPS. So as shown earlier, depending on whether you want the processing system involved, you can choose PL subsystem to just create the basic parts. The CIPS always needs to be involved on the Versal device simply because it needs to configure the programmable logic and enable the knock, but the PL subsystem option will limit the CIPS to the minimal necessary resources. Boot configuration is important for figuring out how to boot. Since this is a development board, there are options for the clock settings. Connectivity to the knock is important, so you can always enable it or customize it. There are a few options for device integrity. And there are different options for PSPL connectivity. Leaving these all at custom means that we're going to configure them in the next few tabs instead of using a preset. So the CIPS has two IPs in it, the CPM and the PSPMC. The PSPMC configuration looks somewhat similar to the menu that you would have seen in an PSOC, where there are peripherals you can enable or disable. IO, more debug options than there used to be for sure. There's the IO tab, boot mode. So yeah, so anyway, since we don't want to manually configure all this ourselves, let's go back. And change a few options to make this simpler. So we're going to enable the knock. Well, that was the wrong one. This changes a few of our other options as well. And we'll set debug to JTAG. Next, we're going to configure the PSPMC. Unlike last time where nothing was set up, there should be a few things selected now. Because we changed this setting to a preset, now I don't have all my options anymore. Presets are good because they abstract a lot of the more granular complexity of these designs, but they also do limit your options. Limiting options isn't always a bad thing. So because of my preset, SD1 and QSPI have to be enabled no matter what I do. Same here. By enabling this preset, I also enabled some of the peripherals that are connected to the NOC. And have set up my IO. So now that I've finished that and applied that preset, it can take a little while to customize. Next, we'll validate this design. So unlike the MPSoC, you don't actually need to connect everything in order to validate a CIPS design. We will save the block design with our new configuration. Then we need to create an HDL wrapper. Typically, Vivado should automatically handle this for you, assuming you don't change the option. This creates a HDL file in your target language, Verilog in our case, that includes the block design now. At the top level, the tool will always require an HDL file to run synthesis on. Next, we want to generate the IP output products. Out of context per IP means that it'll do one IP at a time and won't update everything just because one of them changed. More complex IPs can take some time to generate because it has to perform an out-of-context synthesis on this, which can take a minute. Okay, so at this point, the rest of the steps with the Vivado project are going to take a while. So once this is done, since this should only take a minute, I'm going to run synthesis and implementation. And while we're waiting for that, I will go do the Vitis part of this lab. The goal of this demo is to show the process for making a hardware design, importing that hardware design into Vitis, and working on software for that hardware design. Since this doesn't seem to be finished in the next few seconds, we will then go to designing with Vitis. Done. It should be done. Sometimes it takes a minute for Vivado to update, and while Vivado is running a command, you do not have access to running another tickle command, unfortunately. So until this finishes, can't really do much about this. As you can see, most of the options are grayed out. So to keep things simpler, I'm going to cancel that, and we're just going to generate the device image. And this will go for a while, and in the meantime, we will look at Vitis. So since this is an empty workspace, there shouldn't be any projects there when I launch. If I open in an existing workspace, it will open all projects in the sidebar that were there to start. My virtual machine has very limited resources. That's one of the reasons why things are a little slow. So we are now going to create an application. Theoretically, I should create a platform here, but because I don't have my XSA yet, well, let's see. So we're going to create an application project. I think yeah, good. Okay, so there is a pre-built XSA that I'm going to use here. So this is the XSA that would have been produced in Vivado and will whenever it's done. So I want this to run on my APU on the first core, so the A72 core 0. This is very similar to what we did in the last one. I'm going to need a new project. So we're going to call this Hello World. Yeah. This will be run as a standalone app on the domain. We're similar to the last one. And we will keep the template this time. So I see a question in the chat. As for this, first I saw a question, is the Vitis software emulator not available for Windows? QEMU is typically a Linux application. You wouldn't want to run it on Windows. There are many of the more extensive elements of Vitis development that Linux is more conducive for. Another question was, if I had .xsa, I chose application instead of platform. Why? Because to be honest, you can, as you can see here, when I created my application, I also created my platform. If I only have one platform in the project, I actually can create the platform while creating the application process. Platform creation is more useful if you wanted to create multiple platforms, for example. So it's a good way to just create your platform independent to your software. Another reason to create the platform first would be, let's say you have your hardware, but you don't have any of your software. So there's nothing to put in the application project. You can still create your platform and modify it to understand what your hardware is going to look like to the processor. So in short, yes, you can create your platform through your application, but sometimes it's good to get a better understanding of your platform and to create the Vitis project without being dependent on the software. So now I have a Hello World project. If I look at this template, what I'm going to see is a Hello World source project. This is a relatively simple project, as you can imagine. It says Hello World. It also runs some commands in order to initialize and clean up the platform in order to run on. You can see more information about the platform in these platform files. Because this is a Hello World command, the only thing that's really relevant here is the ability to initialize the UART. In the meantime, looking back at our Vivado project, this is almost done. So the long and short of it here is that what we did here with the Versal devices are just a more sophisticated example of the things we showed in the first couple demos we did, using Vivado to generate a hardware project, and then using the XSA file in order to create a software project customized. Also, we also showed using a template for this. So let us run QEMU now. We'll run on an emulator. So here we have a Hello World. We'll take the app, we'll select Run As, and we'll start the software emulator. If you were doing hardware debug, you'd select one of these other options here. Typically, I usually use the regular launch hardware on hardware, but for now, we're running on emulator. I think I'm in the wrong perspective. Looks like there are some problems with this. So here we're going to see the configurations. So when we go to run, we have run configurations. We can configure a number of different things here to make a custom configurations if we would like. Oh, yeah, okay. So the software emulator failed because I did not build. If you don't build your software, you can't emulate it. See a question in the chat, will QEMU simulate the other devices on the SoC or only the APU RPU? QEMU will not generally simulate anything on the hardware side. There is a topic that I think we've had webinars here at BLT on called cross-triggering, where you may be able to set things up so that your debug on the processor side corresponds to your debug on the hardware side, but those are much more advanced topics. QEMU will not inherently simulate anything about the hardware. That's one of the main limitations of QEMU. It won't tell you very much about the hardware. Where QEMU really bails you out is when you're trying to figure out if your bootloader will boot or not. That's when QEMU is at its best. QEMU is great for software debug if it isn't hardware dependent. The cross-triggering point, by the way, is not about QEMU. That's more hardware debug using ILAs and similar debug tools and hardware. Versal devices have a lot of interesting debug capabilities that older generations did not, that may be worth exploring. Anyway, so now that I think this should be built, now I can emulate this. So we'll go back here. Notice how there's no emulator for the system project. You can't emulate a system project in QEMU. You gotta emulate the application project. You can emulate a system project on hardware in the right situation. So now that I built it, this should work this time. Could take a minute. This is moving very slowly, by the way. As you can see, if you look all the way in the bottom right, you can see that's launching the debugger. Since Versal devices are complex, sophisticated devices, sometimes it takes a minute. Plus my virtual machine is a little low on resources. I should stop this. Okay, so here we have this design run almost finished, by the way. So write device image is the final stage. For a Versal device, instead of a bit stream, it's the device image and the PDI as opposed to the .bit or the .bin. But that's definitely taking up resources. Anyway, back to QEMU, we can see that my software application successfully ran on QEMU. And if I were to take the boot image that this device generated and put it on a platform, must be really low on resources, huh? Sometimes when your computer is low on resources, Vitis is a pretty intensive program. All right, looks like Vivado is finished. Then you can open the hardware manager if you had hardware, which I do not. And then configure the device using the PDI. Once we close this, Vitis should be more responsive. One thing I do want to highlight is this will create a boot file. It'll create a number of binaries here. So yeah, there's the process for creating a software standalone application to run on the Versal device. You put the CIPS in Vivado. Then you build the project, you export the device programming file. You create a platform based on it, which sometimes you can do as part of the application project, and then create an application project. I do want to show another thing in Vivado. I just want to close Vitis first. My virtual machine resources are a little limited. Vivado and Vitis at the same time is pretty taxing. This should work in a second. All right. I'm just going to restart this in a second. All right, I'm just restarting this momentarily. There was one more thing I want to show off about the Versal device project. But what I want to show is how to put a NOC in a project and what connecting to the NOC looks like. All right, so here we are. We'll start Vivado. Because I was a little disorganized in my CIPS project, it created everything on the desktop. Consider this a good instruction on file management. You definitely want your files to be stored in the right place. There we go. But for now, I'll just leave it. So let's go back to the CIPS project. And we'll open the block design again. So to use a NOC, you put a NOC IP in the block design. So we'll open this up. There are multiple options for a NOC that are configurable. I could put an AxiStream NOC in if I want to connect an AxiStream peripheral. This will allow me to connect to the NOC via an AxiStream. Typically, you can't connect an AxiStream directly to a memory map processor like this. So what this NOC is really more for, takes a minute to cancel. The real use case for this NOC is to connect to other AxiStream peripherals. One good example is that if you have a custom peripheral that is AxiStream that you want to connect to a memory system, for example, and write a lot of data to the memory system, you can connect this AxiStream NOC to your IP and have it write to the device. All right, so for example, if I were to say use one of these, I think that's an AxiStream. Okay, never mind, wrong. That was the wrong I2C. The IP catalog has actually changed a bit between different devices. So for example, due to the new hardware on the Versal devices, So this is the main use case for a NOC, where I will have an IP like this Fourier transform and then connect it to the NOC, which will then be connected to another device that's also attached to the NOC. The main use of this is to use the hard interfaces on FPGA. So just to go over what we've covered in these demos and what we've covered today. The process for designing for an embedded system in general and for a Versal device in particular is to start by designing a Vivado hardware project that has the core elements in it. For a Versal device, this will always include the CIPS. Once that design is finished, export the XSA, the platform, using the Xilinx support archive file, import that into Vitis, and then start designing a new application process based on that. There are more sophisticated applications as well that we're not going to cover today, such as hardware acceleration and more advanced types of software design. All right, so that was all the demos that I had in mind to cover today. So.
All right, so we're gonna open it up for Q&A. So if you guys have questions for everything that you learned today, Nathaniel is here to answer your questions. Before we get to that, I just wanted to let you know there is a survey that I will be sending out about this workshop. If you would kindly fill it out. Our entire executive team reads every survey. So if you have opinions about our training, please share them. We will use them to constantly improve our training so we can provide the best possible no-cost events. And also we do surveys for our paid training as well. Do have a look at all of the classes that I have put into the chat panel. They relate to everything that Nathaniel has talked about today. We have our HLS class next week. We have embedded hardware bootcamp coming up in September, as well as the Vitis model composer, and then our Versal training is starts in February. Additionally, if you'd like to check out our website, we've got a ton of no-cost events coming up. In September, we have 2 webinars. One's on verification and another one is on outsourcing for defense contracts. In October, we have a no-cost workshop for managers that's on adaptive computing for managers. And then we've got other stuff coming up like advanced debugging and AXI and space RF socks. So please check out everything that we've got going on. There's a ton, and I hope that you can join us for all of that. So now I'm going to kick it over to Nathaniel to answer any of your questions. So if you have any, please put them in your chat panel, and he will be happy to answer whatever you have.
Sharon, somebody wanted to know about the presentation emailed.
Sure. So we don't provide the slide decks, or as we call them, books, to our no-cost events. However, we will send out the video. It takes a couple of days for that to process, but I will email you the video. Do we have any other questions?
Can you use the NOC? Someone asked in the chat, can you use the NOC to connect the other devices on the board to the PL? Yes, that is the biggest strength of the NOC, the ability to have all the elements of the Versal device connect to each other through the NOC. So for example, if you had a memory device, you can use the NOC to connect something in the programmable logic to that, or anything similar. And this is done through the NOC IP and the IP integrator. After exporting, somebody asked, after exporting the new HDF was the old version of XSAs. So in HDF before 2019 was what XSAs were called. Sometimes it's not updated in Vitis. How to fix this? So let me open the Vitis project again. I could show you. The gist of it is you right click and select update. HDFs and XSAs mean the same thing in different versions, so it's a perfectly good question either way. So let me open. Oops. Sorry, I just want to get back to Vitis. Someone asked, I alluded to a design flow that involved designing without a platform. Sorry, I'm not sure exactly what you mean. There will always be some sort of base hardware design that needs to be used that will string everything together. So I'm not sure exactly what you're referring to, unfortunately, sorry.
If you could elaborate more on that in the chat panel, maybe we can answer that question a little bit more thoroughly.
Does Vitis have linked folders so multiple projects can use the same source files? Yes, you can have multiple projects using the same source files in Vitis. Sorry, this is just starting up. So if you wanted to update the XSA, so that chart that had the 4 design flows, let me see.
Nathaniel, can you read the comment out for everyone, please?
Sorry, before I get, sorry, I'm doing 2 things at once, my apologies. Yeah. Let me finish the first one. So the first question was, how do you update the XSA for if the XSA has changed? So if I go to the platform project and right click, there is an option called update hardware specification, which will open a window in a second, I think. This. You can also do it through the app, honestly. Oh, okay, so it's still initializing, but it will, in a minute, it'll open a window that says, that will let me choose a new one. There it is. So yeah, so right click on the platform and select update hardware specification. And then select the same XSA again, and this will update it. As for the other question, there was a slide with a flow chart showing different design flows with and without AI. I think it was shown right before the break. So I think that refers to this chart towards the end here. Just please confirm for me that's correct. It's towards the end. So is this the chart in question? Okay, so let me explain a little about what this means. So platform refers to a special type of hardware design that can have accelerated kernels linked in by Vitis. When this shows a traditional flow no platform, that means the conventional FPGA design where Vivado, where you build a hardware design in Vivado and export a fixed XSA. So no platform refers to no extensible platform. The custom platform and Xilinx platforms that are referenced are extensible platforms where Vitis can add additional kernels on top of them. So the no platform flow is the same flow that anybody who's worked with FPGAs up until before acceleration was more prevalent used. And the platform refers to the extensible Vitis platform.
All right, Nathaniel, we also had a question. Does the NOC have a driver if you were using the Vitis side of the tools, or does the driver handle the computations?
So the NOC isn't a hardware interface that your software would connect to. The NOC is the interconnect that you use to access it. The way the NOC will work is that your software will try to access a memory address across the NOC, similar to a traditional AXI interface. So what will happen with a Versal device is whatever the IP that you're trying to access with will have a driver that tells the software how to use the NOC to access that IP. So it's just a new wrinkle on the traditional driver. The NOC is not an IP that has a driver by itself because the NOC is not specifically trying to be accessed.
All right, do we have any other questions? All right, well, thank you, Nathaniel, for sharing your expertise with us today. We'll be sending out the survey email in a little bit after this workshop. Like I said, the entire senior staff reads those, so please take a minute to fill out your comments. As a reminder, we will send out the recording of today's event in a few days, so look for that in your email. And we have several related courses coming up, which I will include in that. So also check out our website, bltinc.com, to see our complete training calendar. And we really appreciate you for joining us today. And we look forward to seeing you again at future events. So thanks, Nathaniel.
All right, thanks, Sharon. Thanks, everybody.